Great. Well, thanks a lot. I'm very excited to be here giving the inaugural lecture of the inaugural summer school in Athens on natural language processing. So I have a lot of material to cover today, so I'm just going to jump in. It's going to be a little blunt, but I think this is kind of a critical lecture. It'll kind of seed and get everybody out on the same page for the subsequent lectures. So this lecture, we're going to talk about classifiers. And this basically means building systems, so the sort of underlying mathematical machinery for building systems where we take some inputs, and these are text because this is a summer school in natural language processing, and we produce some outputs. And we're really kind of focusing on cases where the outputs are discrete. So here's a few examples that you may or may not have used in your everyday life. Given a word in some context, try to predict what its part of speech tag is, right? So is work in this context a noun or a verb? That's a very sort of typical classical natural language processing problem. In your inbox, there's probably some classifier in there that takes incoming email and says, is this spam or should I just send it on to the inbox? Or even doing smarter things like trying to say, this needs an urgent reply or this is important, things of that nature. On your assistant, most modern assistants have some sort of pre-classifier that just tries to say, like, what is this person trying to do? Are they trying to set an alarm? Are they looking for an answer to something? And this is just a classification problem over the input utterance before the system does something a little bit more complex. So these are all sort of examples of the problems that, the math that we're going to look at today is aimed at solving. So actually, now that I speak about math, there is going to be math. So the course today is really about machine learning fundamentals as opposed to like building specific applications. So we're going to focus on what it takes to sort of represent inputs and learn from those inputs as opposed to building a sentiment analysis classifier or something like that. Though I will motivate it throughout with various examples. I just want to point out that if you miss a detail, don't worry. These slides are going to be online. Actually, maybe right after the lecture, I'll put them online. And in the interest of time, for some of the more detailed proofs, I'm just going to kind of leave it for people to look at later. I put it in the slides just for completeness, but it's not necessary that you understand the detail of every line of every proof today, right? I mean, the main thing to get out of today are the broad concepts, and I'll go over what those are. All right, so this lecture is about 2/3 linear classifiers. And why? Everybody uses neural networks, deep learning, what have you, but actually understanding linear classifiers is critical to understanding modern neural networks. And actually, in any neural network, the last layer of that neural network is almost always a linear classifier, and it's actually probably the part of the neural network where most of the action is. So understanding the fundamentals of linear classifiers is important for understanding neural networks. And also there's things like, the theories better understood, the optimization is better understood, things like that. So it's kind of a nice introduction to these problems. But we will, in the last hour, dive into neural networks. And just to kind of point that out, right, so this is probably a diagram that you've seen, about a neural network. You have some input, it gets fed into these neurons, these deep layers, and then there's some output on the side. Well, this last bit here, that's a linear classifier, and that's what we're going to focus on here. The main difference between linear classifiers and neural networks is where linear classifiers do multiple transformations on the data to generate this last layer from which we're going to make a classification. Instead, in linear classifiers, typically we take an input, which is a document or a picture or whatever it might be, and we sort of hand design some features that will go into this green layer here that we're going to make predictions. So before I dive into some of the more details, let me just kind of start with an example to kind of give you the idea of what classifiers currently can and cannot do. So let's say our task is to build a fake news detector for quotes or articles, right? So is this article about something that actually happened? Did someone actually say that piece of text, right? So this is a binary classification problem in that there's only two outputs. It's either true or it's false. For some of these cases, even a computer can do it, right? Like, these are very obviously not true, and there's reasons in the text around that, right? Like, people don't adopt babies, and people don't come back from the dead, right? So a computer, even today, would be able to separate these out from, news from the New York Times or things like that. And even when you get to things like looking at images, obviously, like, computers are really good at telling the difference between, like, a tabloid newspaper and something like the New York Times. What about this? I mean, did Elon Musk actually say this? Yes, he did, right? But like, if you look at the text, he's talking about like summoning the demons. It sounds like something from Lord of the Rings, right? So a computer to be able to make this classification just by looking at the text is kind of tricky, right? Even though it's true, he did say this. This article is true. It's a little easier, right? It's written in a prose that's a bit more professional, a bit more news-like. But even then, there are elements of science fiction to the task. So can we teach computers to do this automatically? Actually, some people in this room work on this problem, and it's extremely hard because the information doesn't just lie in the text itself. We need like a lot of information about, background information, what these entities do, common sense knowledge, things like that. Another task, which is much easier, is topic classification. So given a news article, determine, is it about politics, is it about sports, is it about technology? So the input is a document here, and the output is some finite set of labels, which are our topics. And modern machine learning methods can do, depending on what the taxonomy of topics is and how fine-grained it is, we can do really well on this problem. In some cases, high 90s, like basically almost solved in some cases. And you can see why that's the case, right? Like this article here, well, whether it's true or not, it's definitely about technology, right? It's not really about the weather, for sure. Just looking at the text, it's a very simple classification to make. So why can we do that, and how can computers do that? So I want to just do a very simple exercise here. So for people who are a little bit familiar with machine learning, this will be a little basic, but I want to sort of get everybody on the same page. So, right, a computer doesn't know English or doesn't know the language that you're building a classifier in, right? But it can still learn to make classifications. So here, there's a language you don't know how to speak. It consists of stars, diamonds, circles, hearts, and triangles, right? And there's some labels, and you don't know what those labels are, right? We haven't sort of grounded them in some semantic concept, right? It's not like politics, sports, or whatever. We're just saying it's -1 and +1. You don't know what those labels mean, right? And now I show you 4 sequences, 4 sentences from this language, and I tell you how we classify each of those sentences, right? Some are -1, some are +1. So now I'm going to give you a new sequence. So you've learned something, and now we're going to go into the wild, and your classifier that you've just learned, we're going to apply. So what's the label of this sequence? -1. That's easy, right? Because, well, in our training data, there was the exact instance, right? Star, diamond, circle was the first instance. It had -1. Pretty easy. What about this one here? Also -1, right? And you learn that because, well, stars are sort of more correlated with -1. Diamonds, kind of 50-50. And a heart only exists for -1. There's no +1 example that has a heart, right? What about this case? +1. So actually, okay, good. It's a little bit, this one's a bit trickier, and I'll show you an example, but you guys probably did the right thing when you made that classification. So why can we do this, right? The simplest thing to say is like, okay, well, I have some conditional probability distribution, the probability of a label given that I've seen one of the symbols, right? And so for the first case with -1, clearly star occurs more in -1, correlated more with -1, and heart definitely more with -1, right? So if we multiply those probabilities, -1 has a higher score. But this one here, everybody said +1, and that's the right answer. But when we make that kind of independence assumption, so this is an independence assumption that the probability distribution is independent of the entire sequence, we factor it by individual symbols. Actually, that model wouldn't be able to distinguish here, but there are features, right? Basically, like star and triangle in that position. So first of all, triangle in position 2 only happens with +1, right? Star and triangle as a bigram, you know, right next to each other in the sequence, only happens in +1. And circle, that doesn't really make a difference, right? It happens once and at the end of the sequence. So this is machine learning, right? Basically, what do? We define some model of interest, the probability of a label given the sequence. We made some assumptions if needed, right? Here the assumption was that that probability factors into probabilities of individual sequences. And then we fit the model to the data, and that was the counting part there. We basically just counted how many times we saw those events together divided by the number of events. So that's it. My lecture's over. That's machine learning. Well, fortunately, we've moved a lot beyond that. So we're going to spend a lot of time sort of focusing on you know, when we can prove things about these learning algorithms and sort of principled ways of optimizing these sorts of objectives. So let me jump into the nitty-gritty. Really feature representations. So how do we represent inputs, but also the terminology and notation that we're going to need going through the lecture. So here is where the details really start to come in. So if something is not clear, this is not a one-way conversation. Please raise your hand, stop me. That's totally fine, okay? All right, so we're going to use X as inputs. So this bold X represents some input, typically a piece of text, a document, a sentence, a word, and that comes from some space of potential inputs, which in the case of documents or sentences is not finite. In the case of words, it usually is. And then the output that we want to predict from the classifier is going to be a bold Y. So this is this label, right? In the case of topic classification, it was sports, politics, technology, and that comes from some set, capital Y. And this set is finite for sure, and usually it's quite small, though it need not be, but it's definitely finite in this case. A very useful concept is this idea of an input-output pair. So when we pair them together, right, some input associated with some output. Whether that output Y is the true output or an incorrect output will depend on the context, but having this notion of pairs of input-outputs is going to be important, right? So this is a news article with a topic would be an example in this case. So we are going to exclusively, well, primarily focus on supervised machine learning. I'm going to talk a little bit at the end of the course about semi-supervised learning and unsupervised learning. But in supervised machine learning, what we assume, just like the sort of thought experiment we went through before, is that we're given some labeled training set. So somebody has labeled some examples of what we want the classifier to do, right? So these are pairs of inputs X and outputs Y, right? And we have capital N of these pairs. So this is our training data. This is what's going to go into the machine learning algorithm, and out of the machine learning algorithm, we're going to get this classifier. So you can say, okay, this classifier is age. It maps from some input, the input space X to the output space Y. And what we really want to do, what we want our models to be able to do, is to pick an H from the space of all possible H's, so all possible classifiers, such that it generalizes Y, right? Or sorry, generalizes well, I should say. So if I make a prediction Y hat from that function H, well, hopefully Y hat is as close as possible to the correct label, you know, most of the time. And usually we measure that by looking at the training data or some other data set to compute that. Good. So this setup really can go by a bunch of different names that you'll see in the literature and online in different slides. And it really depends on what Y is. So Y doesn't necessarily have to be a discrete set of output labels, even though that's what we're focusing on today. It can be just a real value. So this is regression, right? So the input, we have some document, and we output some real value. So maybe the input is a consumer review of a product, and I want to say on a scale of 0 to 5, you know, how much did that person like it? That might be a natural language processing example. In many settings, we want a vector of real values, right? So maybe you're given a document or some entity, and you want to sort of predict coordinates of where that lives in some space. That comes up not that often in natural language processing, but in other areas. Discrete outputs are really what we're focusing on, as I mentioned. And the first two are what we're going to talk about in this lecture. So binary classification, really +1, -1, is something true or is something false. Multi-class classification, we have K different labels, right? So this is like the topic classification. We have politics, sports, technology, religion, what have you. But again, finite and small. And actually, we really will primarily be focusing on multi-class classification because it obviously subsumes binary classification. Having binary classification as a separate concept is useful because sometimes it makes the math a little bit easier. But ultimately, if we really want to build good classifiers, we really have to focus on multi-class classification. Tomorrow, I believe, we are going to look at structured classification. So this is the case where you don't want to just predict a single label for an instance, but you want to predict a set of labels. And that set of labels is usually, the size of it is correlated with the input. So maybe machine translation, right? A label here is a word, the foreign, the target language words that you're trying to predict, and you need to predict as many of them as you need to create a sentence in that language. But there's a lot of other examples that we'll look at tomorrow. There's obviously combinatorial issues when you start looking at structured classification. Okay, so in linear classifiers, feature representations are critical. We have some input, and we need a way of transforming that input into something that a classifier, a piece of code, a mathematical model can do something with. Obviously, we can't just pass in some UTF-8 string. It has to be, in a language that the computer can understand. So there's that aspect of it, but there's also sort of like how do you design these features conceptually, things like bag of words features for text. I'm going to talk about that on one slide. But an image, like looking at pixels, looking at SIFT features is sort of a popular thing in image classification. The core of machine learning NLP research, I would say up until about 2015, really focused on designing good features for linear classifiers. So it is a very important aspect of the work. So what does it mean to sort of transform a input, which is a string, essentially, into a feature vector that a machine learning algorithm can do something with? So here we're going to define this transformation, C of x, right? And this is a function that maps from the input space x, here, again, strings, some text, to a real valued d-dimensional vector, right? So we're projecting to some space of d dimensions. And there's no real restriction. Certainly, from a theoretical standpoint, there's no real restriction on what this looks like. But typically, we make assumptions about it that make learning or even just conceptually dealing with it easier. And in particular, for linear classifiers in language, we often assume that that vector, even though it's a real value d-dimensional vector, it's binary and it's sparse. And that means the values are 0 or 1, and they're almost always 0. And I'm going to show you an example for how that happens. And generally, in the example I'm going to show you, categorical features. So, not just like is something true or false, but does a feature come from a set of possibilities, can be converted to binary features anyway. So it's a nice abstraction. And later in the lecture, we're actually going to look at cases where that real valued feature representation is dense and it is real valued. We're using the full space. One useful notion, in particular with multi-class classification, which is what we're going to focus on, is actually not defining features just over inputs. So not mapping from inputs x to some real valued feature dimension, but mapping from input-output pairs, right? So basically, I'm going to define another function, phi of xy, which will take an input and a potential output label for that input and map that to some feature space. And you'll see in the math, this kind of just makes things a little bit simple, but I'll show you that actually it's an equivalent representation doing it one way or the other. Well, sort of equivalent. So to give you an example of what these features might look like, so let's assume X is a document and Y is a topic, right? So this is that topic classification. I have phi, so I'm going to work in the space where I'm mapping to a sparse binary feature representation over inputs and outputs, right? So this is quite simple. So let's say one feature I can define, the jth feature in this feature representation is 1 if the document X contains the word interest and the label is financial and 0 otherwise, right? So it's very simple. You just write some if-then code to sort of map from a string to a value in a feature vector. Again, it doesn't have to be binary and sparse. You know, you could say like, well, okay, one thing I might realize is that like documents that have a lot of punctuation in them tend to be more likely scientific because formulas and numbers, you know, have additional punctuation as opposed to just end of sentence. So maybe I can say like, okay, well, the percentage of words in a document that has punctuation, you know, that's a useful feature to have. It doesn't necessarily have to be a whole document. We can have something simple like, okay, we have a word X and we want to give it a tag, a part of speech tag Y. So is it a verb, noun, adjective, things like that. And you know, one useful feature might be like, well, okay, if the word ends, if it's English and the word ends in ed and the label is verb, that's a useful feature, right? We would expect that like a system would rely on a feature like that to make this classification. Is this visible? Yeah, okay. So this is what is called a bag of words feature representation. So taking this one step further. So here X is an entity, a name, so some kind of name, and Y is the label classifying the type of entity here. So right in this example, we're looking at basically either the name is a person or the name is a location or an object or something of that nature, right? And what we're going to do is define a feature space of dimension 8. And this is, again, the joint feature space of inputs and outputs, right? So the 0th feature is 1 if the name contains the word George. The second is 1 if it contains Washington. The third if it contains bridge. The fourth if it contains general. All conjoined with that the output has to be person. And then we have a basically symmetric version of those features where all we've changed is the label that is being conjoined with, right? So location instead of person. So a bag of words feature representation takes an input like X, which has a bunch of words. It splits it into words and a label Y, and it creates this feature representation, the sparse feature representation from that. So this is a bag of words representation. It's binary. Basically, there's a 1 in spots where that, if that word exists, and a 0 in spots where that word doesn't exist in the input X. And here, of course, depending on the label Y that we choose, certain blocks of that feature representation are going to be true, are going to be 1 or 0, right? So General George Washington, the 0th, 1st, and 3rd feature are 1. Everything on the second half of the feature representation is 0 because we're conjoining it with the label person. And so all of these features on the right are just going to be 0. George Washington Bridge and location, similarly. And, you know, we call it bag of words because we'll take something like George Washington George, we sort of throw away the context. We just say, okay, well, George exists in this document, right? It's sort of a bag of words. We've taken all the words and we've thrown them together, and we've lost the contextualized information about those words, and we can see that here. So this is a case where we actually don't even count the number of times George occurs, right? We just sort of say, oh, George, the word occurs in this sentence. I'm just going to say it's true. It's got a value of 1. But you could count it. Maybe you say, like, these features are the number of times that that word occurs in the document. It's a perfectly reasonable feature representation as well. It makes it non-binary, but that's fine. So this is an example of what's commonly called block feature representations. And I described this before. Basically, by conjoining the feature space with the labels, we've ensured that we've divided the feature vector into regions, where each region corresponds to essentially the same set of features. So there's symmetry between input features and regions, but those regions are whether that label is firing for that feature or not, right? So whenever the label is Y, location, the label Y is location, the first block of features always has to be 0, right? So this is why this is called a block feature representation. So what's the difference? We have these two representations, psi of x and phi of xy. Well, they're actually equivalent, right? If I took this representation here, and I dropped the y. So basically the features just say like 1 if x contains George, the second one, 1 if x contains Washington, what have you. So it would be a 4-dimensional feature space because we don't have to multiply by the number of labels. You can basically say like, well, if that's my feature representation, C of x, I can just define this vector E of y, which is a one-hot vector, which means it's 1 in one position and 0 across the other positions, and is 1 in the position for the label that's true. And I could just multiply them together, and I'll get phi of xy as well, right? So these are kind of interchangeable representations. So right, C of x here for General George Washington is 1101, and here's the corresponding phi of xy. They're always 1101. We can just multiply the first one by this E vector, this label vector, to get the second one. So like I mentioned, I won't touch on this a lot, but feature engineering and NLP pipelines is, again, up until about a few years ago was very important, right? So that's not just like on my single classifier, but like a lot of times, let's say you wanted to build a sentiment classifier, you'd first build a classifier that predicted part-of-speech tags for the words, right? Because seeing a lot of adjectives in a document, good, great, bad, whatever, is indicative of that document having some sentiment, not being an objective document. And then those part-of-speech tags would then be features for the ultimate sentiment classifier. So this consumed a huge amount of energies in linear classifier machine learning for natural language processing. So I'll give you an example. This is from my friends at Babel, a machine translation company in Portugal. So here we have some machine learning system, and we want a system that can classify, does this translation look good or bad, right? And this is useful because maybe someone's relying on that automatic translation to do something, like build a report, talk to someone in a foreign country, and we want to kind of give them a score, like how confident are we that this is actually the right translation? And this is the wrong translation. Who speaks French? I forget, what is this? This is, it's like the trials of machine translation or something like that, right? Yeah. Maybe it's a good translation, I don't know. So in the Babel's quality estimation system, here are the features they use. There's way too much to go into, so I'm not going to, but you can look at the slides later. But the ones in red are some easy ones to understand. So basically like, what are the number of tokens in the source and target, right? If I need to use way more tokens in the target, that's kind of an indication I may have done something wrong, or I use way too few, for instance. But that's not always the case, right? Languages are different. Certainly on the syntactic side, right? What are the number of verbs, nouns, prepositions, things like that? Prepositions less so, but certainly nouns, right? If there was a noun in the source, like say there's 3 nouns in the source and only 2 in the target, well, some information might have been dropped, right? So these are the kind of features that go into this classification. And this is, typical case of feature engineering and natural language processing. Okay, so what is our setup? So that's kind of the representations. What is classification? We are going to assume basically multi-class classification. And that's what I'm primarily going to focus on. So basically this label set Y is more than 2 in abstract, and it's finite. Okay, so linear classifiers. What is a linear classifier? Well, they are parameterized by W, a weight vector, which is a real valued vector, again of dimension D. And the reason it's of dimension D, the same dimension that our input features are, is because we simply just do a dot product between this weight vector and the feature representation. So basically our function age, our classification function, is defined as the argmax over all possible outputs, labels, in the multi-class classification problem. And we usually call this dot product here the score, right? So the weight and the feature representation for that particular label, right? So different labels are going to get different feature representations, right? Different blocks are going to have ones in them, depending on the label. And this is just, a linear sum of a weight for every single individual feature, right? So the weight at position I and the feature at position I, right? So these weights here essentially assign some score to that feature, that input feature and output label, right? So the intuition here is that if an input feature is highly correlated with an output label, then the weight for that feature, WI, is going to have a really high score, right? We're going to want to sort of give that label a high score. So that the example of the word ends in ED and the part of speech tag is verb. Now, that's not a perfect feature for classifying verbs in English, but it's a pretty good one, right? So we would expect that our classifier would learn to give that particular feature a high weight. So all linear classifiers take this form, essentially. And, well, not essentially, actually. And the main difference between all linear classifiers is basically different strategies for learning W, right? This is machine learning. We have some parameters W. The feature representations are fixed. A human sat down and designed those features. And now we want to learn these parameters W for those features. And so how do we search the space of parameters W to find the best ones? And that's really what separates different linear classifiers apart. But actually, hopefully at the end of this section, you'll see that the differences are pretty small amongst the most popular linear classifiers, at least. These three here. Okay, so, right, so we have Y, which is a set of classes, and we have a label or a weight Y. So this is, sorry, I should preface this with, this is how linear classifiers work in the joint space, where you have joint features over X and Y. And I want to show you that it's equivalent in the other space where you just have features over X, right? So we have the features over the input. We have the same labels. What we're going to do that's different here is instead of having a single weight vector, we're going to have a weight vector per output label. And basically what we say is that the Y hat, our prediction, is equal to the argmax, the highest scoring label, the weights for that particular label, and the feature representation of X. So the feature representation doesn't change at all here. It's always the same for the input. What's changing over the argmax is the weights that we're going to use. Here, they're going to be indexed by the labels themselves. Right, and to show you why they're equivalent, this is the first case where you have feature representations over X and Y. So basically, these would be our features for General George Washington, depending on whether we're going to label it as person or our object. I realize that was location in a previous slide, but I think you should be too difficult. And we learn a single weight vector here, right? Because the dimensionality of the input representation is 8. So we have a single weight vector of 8 dimensions, right? Down here, we have an input representation of 4. And 1101, that will correspond to exactly one of the blocks in the block representation. And we have two representations. We have the two parameter vectors, W's. One for when the label is person, and one for the label is object. And these are now 4 in dimension. And you can see, if you do that argmax, you're going to get the exact same output, right? So if I essentially took the parameter vector from the joint feature representation, I split it into 2, I could use that parameter vector for the non-joint representation. So these are equivalent ways of representing the problem. They're not exactly equivalent, but I'm not going to go into the details. Actually, the joint one, you can do sort of have much more rich features between the inputs and the labels. But that's kind of a bit more of a detail. You'll often see when reading papers, especially about neural networks, or papers not from the natural language processing community, actually the machine learning community, this notion of a bias. So we often don't say, oh, it's just like an argmax over a parameter vector and some feature representation, but we also add a bias. And that bias, in this case, is indexed by the label. And what this bias tries to represent is the fact that there's usually a class imbalance in our data set, right? So some classes are more likely than other classes. And we want the model to be able to represent that. All else being equal, I'm just going to predict the most likely class. And that's usually not a bad thing to do. And the bias term, which is just a real value, it's a scalar, is a way of actually encoding that in the model. It's superfluous. You don't actually need it. You can just sort of add a feature to your input representation that's always true, right? So if you have the last feature of your input representation is 1 if always and 0 otherwise, then that's a bias term. And usually that's what we do in natural language processing, and we just throw that away from the math. But because we live in a neural network world and we've now used the notation from neural networks, I'm going to bring that back at the end of the slide. So I just want to point out that it's there. I'm going to sort of gloss over it for now, but it's there. And speaking of neural networks, again, this is the notation that people use in neural networks. I will get back to using this notation, but they're equivalent, right? So basically, if I wanted to do sort of an argmax here, right, over different parameters y, I can just say, like, well, what I'm going to do is create this weight matrix where every row is the parameters for every single label, and then I'm going to multiply that matrix by the input representation. That's actually going to give me a vector of scores that the dimensionality is the dimensionality of the labels. Each score is actually the linear score of the label itself. I'm going to add the bias terms, which here is a vector, one for every single label. And I'm going to take the argmax over that vector. They're identical. You know, yeah, people prefer one notation over the other. I will get back to that, but for now we'll use the kind of what I think is the simpler dot product notation. All right, so in binary linear classifiers, just to sort of point out why this is a useful concept to understand or to talk about, y here is going to be +1 or -1. So like I said, we're going to mainly talk about multi-label classification, multi-class classification, but it is sometimes nice to think about binary classifiers. So here, the label, the argmax is only over 2 labels. If we expand this out a little bit, what we can say is that, okay, well, basically it's going to be +1 if the score of the first label, +1 label, is greater than the score of -1, right? So that's simple. This is just, this is how the argmax works. We're just changing it into an if-then statement, right? -1 otherwise. What we can do is actually just rearrange this a little bit, right? Move everything from the right-hand side of the inequality to the right-hand side, group things in the right way, and realize, like, well, actually, we don't need a parameter vector for 2 classes, for the +1 and minus class. We can just say, well, the parameter I really care about is v, which is just the difference between those 2 parameters, and c, which is the difference between the bias terms. And I still get a linear classifier, and now my classification decision is I'll just take the sign of the output of this particular class. If this is greater than 0, then it's +1. Otherwise, it's going to be -1. And this is useful. First of all, only half the parameters are needed. So if you have a huge parameter space, you actually reduce the memory footprint. But it's also conceptually nice. In particular, when you think about geometrically what is a classifier doing, right? We have a bunch of points in space. When you think about the binary classification place where you have a single parameter vector v and a bias term, this is a hyperplane in that space, right? Essentially a line in that space that divides the points, right? Everything on one side of the point, one side of the line is going to be negative, and everything on the other side is going to be positive. So from a geometric standpoint, it's a very nice and easy concept to have. Multi-class classifiers are a bit tricky. We can't say there's like a hyperplane that divides the space. They essentially define regions of space where certain regions are classified one way and other regions are classified other way. In fact, they actually define, it's basically an intersection of half space. I'm not going to go into the details here, but it's linear in W. That gives you basically a half space, and then the intersection of those defines a classification space. You can't get regions that are non-adjacent that give the same label, which is kind of the critical point here. And it's a little geometrically trickier to think about multi-class classification. Again, using this notion, this geometric notion, a very important concept in linear classifiers is this idea of linear separability. And this means that the training data is such that I can find a hyperplane that perfectly classifies all the instances, right? I can draw a line in the space, and on the right of that line, or on one side of that line, are all the instances from one class, and on the other side of that line are all the instances from another class. And this is a very useful concept. And this is, in practice, never actually true. But a lot of the theory does depend on it. Okay, so that is the, almost an hour of preface. Now let's actually talk about what linear classifiers are. And so the perceptron is basically the oldest machine learning algorithm out there. Does anybody claim there's older? It's basically modern machine learning algorithm. Who knows? 1957. That's old, right? Back in those days, things were a bit different, but it's kind of funny. It was developed for a specific architecture, and we are kind of coming back now to those days where we're not developing them for some like generic Intel architecture. We are starting to develop machine learning algorithms for specific architectures. And so it's kind of interesting. We've kind of made a lot of progress, but lost some abstraction in the process. But what I want to point to, and sort of get into the first slides here, like what can our classifiers do? So this is from a news article talking about the perceptron. And there's a lot of news articles today talking about artificial intelligence and what's around the corner. Well, in 1957, they were talking about things like perceptrons being able to recognize people and call out their names, instantly translate speech from one language to another. And these are things that we're just getting good at, right? Like in translating speech from one language to another, arguably we're still not good at it at all, right? I mean, we're a lot better than we were, 60 years ago? But it's by far an unsolved problem. And so I just want to point this out because there's various articles from very trustworthy sources out there, like Wired and things like that, that make claims that they might be true. We don't know. But take everything that you read with a grain of salt in the popular media and even in some papers as well. Okay, so the perceptron algorithm is what we call an online algorithm. So this processes one data point at a time. And the way it works intuitively is we take some input, x, we apply the model, the current model that we've learned. So this is the parameter vector w, the function h. We make a prediction. If that prediction is good, it actually is the gold prediction. We do nothing. If it's wrong, we make some updates. And I'm going to show you what that is. So this is the perceptron algorithm in all of its glory. And this is actually roughly the amount of lines of code you need to implement the perceptron algorithm. For anybody who's ever done it, and I think you will do it in the lab this afternoon, most of the code you write, 95% of it, is actually the code that converts from raw strings to the feature representation. The rest of the code is super short, which is nice. Okay, so here we have the training data D. We initialize it. We want to learn these parameters W, right? This is the goal of the learning algorithm. We're going to say, okay, we're going to index that by some value, which is going to be k. So the 0th value, though, we just set it to 0. All the parameters are 0, but they can be random. Theoretically, it doesn't really make a difference. Now what we do is we're just going to keep iterating. We're going to get a new training example from that data set D. This can be random, or you can see them in sequence. That's not actually super important either. We're going to make a prediction. And so I'm using the joint feature representation here. So get the best label under the current parameters k. So k is sort of the currently where we are. If that prediction is not the right prediction, so if it is the right prediction, do nothing. If it's not the right prediction, we're going to create a new set of parameters. So we're going to update the parameters to k plus 1. That's going to be equal to the old parameters plus the feature representation for the correct label minus the feature representation for the incorrect label. And intuitively, what this is doing is putting weight, right? Because we're essentially saying, oh, if a feature is if feature in this example is correlated with a particular label, we want to add weight to that particular feature and take away weight from the incorrect feature the incorrect label that we predicted, right? This will essentially downgrade the score of the incorrect label and upgrade the score of the correct label for this particular instance. So this is it. This is the perceptron algorithm. We increment k, and then we continue. And there's lots of variants of this. People average the perceptron algorithm. So at the end of training, instead of just taking the last particular weight vector, people will average all the weight vectors they've seen during training. And that there's actually some theory around that. You almost always get empirically better classifiers. But this is basically it. Okay, so what does the perceptron do? And that's nice. At least to me, it's intuitive. If it's not intuitive to you, please feel free to speak up and we can go back. Okay. All right. I'll take your word for it. Okay, so what is it actually doing in theory, right? So that intuitively works. Can we actually rely on it in practice? So there's old work that actually shows that there is some guarantees we can make with the perceptron algorithm. So let's assume that the training data is linearly separable with some margin gamma, right? And what does that mean? So as we said before, that means that there's a way of putting a hyperplane in space that perfectly classifies all the instances in the training input. But sort of arithmetically, one way of saying that is, well, there's some wave vector u, and I can scale away. I can force that wave vector, the norm of that wave vector, to be 1, because the scale doesn't really matter, such that that wave vector, for every gold instance x, y, x of I, y of I, it scores the true label y of I higher than an incorrect label y of I prime, plus gamma. So the gap between the scores of the correct label and the incorrect label is this margin, gamma. And yeah, we say a training data is linear separable when such a U exists. Another concept, which is not really that important, it's just important to have for a proof, is this notion of radius of data, which is basically like the norm of the distance between any two feature representations of the input. And the critical thing here is not what that means, but just that that's finite, right? Because our feature representations are binary sparse features, that the difference is going to be not necessarily binary sparse, but finite, and the norm is going to be finite as well. So based on this, there's a very famous theorem from 1962 that says, well, basically, if the training data is linearly separable, the perceptron is guaranteed to find the separating hyperplane, because there might be multiple, after at most r squared over gamma squared mistakes. Both of these values are finite. So this means that in a finite amount of time, the perceptron will converge to a separating hyperplane. So this is kind of probably the first learning theory result ever that's sort of given a training data and a particular algorithm, we can sort of say that that algorithm is satisfying some property on that training data. And here that property is minimizing error, right? It's minimizing the amount of classification mistakes that it makes on the training data. I'm not going to go into the proof, but it's actually quite simple. You basically lower bound and upper bound two values and solve for them, and you get this mistake bound. The arithmetic is pretty easy, so look at it offline, and if you have any questions, ask me about it. Feel free to send me an email if you like. Okay, so that's great. That sounds like the perceptron is this super awesome algorithm. We should always use it. But we have to remember that the decision boundary is linear, so there's only certain things we can do with it. Certain data has to have certain properties. And actually, we can take a very simple set of functions and show that it breaks down. But the perceptron, like if our function is OR, so let's say our input space is of dimension 2. We have x1 and x2 values. And let's say it's binary, right? x1 is true, or x2 is true, or both are true, whatever. Well, we can plot, for a given function like OR, we can plot the data, right? So triangle means true, and circle means false, right? So when x1 or x2, when they're both true, then we get a triangle in the upper right corner. When either are true, we get those two opposing triangles, and then when they're both false, or is false, right? And yeah, we can separate that with a line in space, that's fine. Similarly, any AND function we can do, even cases where we negate some of the properties, right? So when not x1 and x2 is true, that's the triangles and circles there, and we can draw a line through that space. However, for the XOR function, a perceptron, if given training data, in this case, which would be 4 data points, it can never actually perfectly classify this data. And that's because, right, XOR is false when both x1 and x2 are true. So we get a circle up there. And there's no line in the space that would perfectly classify these instances. However, and this is basically nonlinear classifiers in a nutshell, we can just change our input representations. We can make the observation that XOR is actually equal to when X1 is true and X2 is false, or when X1 is false and X2 is true, right? So we can join our features in a way, and that's what we have here. It's not defined in one of the spots, but the nice thing is we sort of projected our input to a different space that's equivalent. It still is an XOR function, and now we can throw a line in there and classify it properly. So this is actually one of the feature engineering in NLP basically focused on trying to create these representations so that linear classifiers can do a reasonable job at classification. Okay, well, is it any good in practice, right? This is all nice and good, but actually it turns out until about 2014, I would say, for almost any task that you were doing, it was basically state-of-the-art or close to state-of-the-art, which on the one hand sounds kind of sad, that like there was no progress since 1957. That's not really a true representation of the situation, because most of the field actually focused not necessarily on the machine learning algorithms themselves, but the representations. How do I take my input and how do I represent that with rich features, take all sorts of knowledge engineering and what I know about the world and augment those features so that a simple classifier like the perceptron can do a reasonable job. Okay, so that is the first linear classifier. Any questions about that? All right, yeah.
Hello. So about the linearly separable, with the XOR, right, like you can like separate, right, like you can like maybe raise two of the points, right,
Yeah.
and then you can, so what was never clear to me is that, so for a particular problem, can you just say whether it's linearly separable or not? Or all depends in the representation? So can you say this problem is linearly separable?
No, it's dependent on the representation.
Okay.
So certainly it's dependent on the representation. That said, I actually don't know the theory well enough, whether there is a case that you can prove that there's no way of changing the representation to make it linearly separable. Yeah, but it's highly dependent on the representation.
Okay, so if I...
Yep.
Is it okay?
Yeah.
What I wanted to understand is why do we add sometimes nonlinearity to the neural network? Is it because the problem as it is will not be separable, so we have to add the nonlinearity to make it separable? Or could I find a way of not adding nonlinearity but still make it separable by doing some other kind of transformations?
But those transformations they're the same as neural networks, essentially,
Okay.
right? So, whether we take our inputs and by hand we write out new features that conjoin or do different things to sort of project that feature representation to a different space. In SVMs, it was very popular to use kernels. I don't actually have time to talk about that, but I will point people to some slides here. That was sort of the mechanism there to do that. And again, it was a linear classifier and was just projecting that space. And neural networks are doing the exact same thing, just with a different mechanism, right? They're taking some inputs that may not be linear separable, and through all these transformations, as well as nonlinear squashing activation functions, are doing this nonlinear projection to a new space that hopefully we can classify. Yeah.
Okay.
That said, there has been kind of a change in attitude. People really worried about these things with linear classifiers and optimization. People thought it was like critically important to understand, things like generalization error and, what is exactly being optimized. Neural networks has kind of thrown all that out the window a little bit. Not that people don't think it's important, but people realize that it may not be the low-hanging fruit. A lot of these things aren't fully understood in neural networks.
I did not get very well the notation argmax that you used.
Which one is this?
No, a few slides before. Oh, yes, that one.
Yeah.
In the prediction, you say.
So you didn't understand what the
argmax.
What that actually means, or?
Yes.
Oh, I'm sorry. So basically what this means, so this is a function that says over this, so like, max would be the actual value, right? If I said max of y in this set, this function, you get the actual score itself, right? The highest score. Argmax means don't return the score that's highest, but return the label that has the highest score, right? So the argument from that set y that has the highest score. So there's kind of two things going on here, like find the highest score, which is the max, and then return the label that corresponds to that max score, the argument. Does that make sense? Sorry, I should have actually explained that. I've maybe assumed that was common knowledge. But here all this is doing is, instead of a max function, just returning the label that has the max score. Right. So if I had, let's say, just to sort of make that concrete, let's say I had 3 topics: politics, sports, and finance. And then for a particular input, politics had score 2, sports had score 3, and finance had scored 1. The max would be 3, the highest score, and the argmax would be sports, the second one, the second index that corresponds to that max.
One thing that you didn't comment too much is, what if you cannot separate the linearly the set? And that seems to be the really interesting thing about what will happen with perceptrons.
Yeah. So I will get there. I'll get there. But what you can actually show for the perceptron is that it is optimizing something called the hinge loss, which is a convex function. And it's basically, it is still minimizing errors on the training data, even in the case where it's not separable. So there's a little bit of theory there. For perceptron, it's not great. For things like SVMs, which I'm going to get to, that theory is a lot stronger. Okay, logistic regression. So this is I will point out that this is a critical section, because when you get to neural networks, especially in later lectures, the last layer of most neural networks is a logistic regression classifier. In particular for machine translation and things like that. So this is particularly important. So where perceptron, we sort of said, okay, well, the score of a label and input pair, that's just a raw score. It's some real value. It's a scalar. We really said nothing about it, what scale it has to be on. The perceptron algorithm basically just says, okay, as long as I'm putting higher scores to correct labels and lower scores to incorrect labels, and that's a good thing. As long as I can classify things well, I don't really care what the score is. Logistic regression is a probabilistic model. So we actually take this score, which is the same. It's a linear classifier, parameters W multiplied by the feature representation, and we exponentiate it and we normalize it. So the normalization function is just the sum over all the labels in the set, the exponentiated score of that particular label, and we get a probability distribution, right? So it's still a linear classifier, and you can see that's a linear classifier by simply just sort of following functions in the argmax. The z of x, which is called the normalizer, the partition function, is the same no matter what y is, so we can throw that out. Exponentiating something doesn't change the max value, it just scales things, transforms the inputs. We can throw that out, and we get a linear classifier on the bottom. So logistic regression is still a linear classifier, but we've just put it through this transformation to turn it into probability distribution. And this is useful in a lot of settings. First of all, from a theoretical standpoint, but also even from a practical standpoint, because it calibrates the scores of the classifier, right? Instead of just being some value, real valued scalar, you actually can say something about it. With 80% probability, I believe that this label is true, right? It kind of grounds the classification itself. So this is a softmax transformation. Basically taking a dot product or some sort of linear score, here just the dot product, some affine transformation, something like that, and normalizing it to be a probability distribution in this way. It's called the softmax transformation, and it's something that we're going to talk about when we get to neural networks as well. But when I mention it there, that's what this is. Okay, so given that we have a probability distribution, well, how do we learn the weights W? So we're going to get more into, I would say, principled convex optimization, right? We have we're going to define a function that we care about, and we're going to try to optimize it. So with logistic regression, as is the case with a lot of probabilistic models, we're going to try to maximize or minimize some notion of likelihood. Here, we're going to minimize the negative conditional log likelihood, or we could just maximize the log likelihood. The negative is just that negation sign at the front. So what is the log? So let's first talk about likelihood, right? That is this term here, right? So we take, for every single instance in our training data, so every xt, yt pair, which is the gold instances, we basically want, so in the maximized setting, we would say, okay, well, we want the probability of the correct label to be as high as possible, right? So if we're maximizing, we would say, like, okay, well, a good thing to do would say, I want this function to be maximized. So over my training data, the probability of the correct labels given the corresponding inputs, I want that probability to be as high as possible. The log likelihood is, well, I just throw a log in front of it, and that is a mathematical convenience and nothing else. Basically, it allows us to turn this product into a sum. And then I also make it negative, and this is, again, not necessary. But since we usually talk about convex optimization, we're often talking about minimizing functions, not maximizing them. But like, it's symmetric. There's nothing magical going on with that negation. So right, this is the negative conditional log likelihood. We can, again, push that log inside the product and make it a sum, which is nice. And then we can expand that a little bit. So the math isn't here, but basically, if you just take that probability, you expand it there, you do a little bit of arithmetic, you're going to arrive here. And in particular, we get rid of the negation as well by arriving here. And so what this is essentially saying is this is a function where I say, okay, I want to find a weight vector W such that I want it to be the one that minimizes this function. And on the left here, I'm essentially saying I want the score of all, I want to minimize the score of all instances. So this will, of all labels. So this will actually include the correct label. But on the other hand, since I'm minimizing, I want to maximize the score of the true label, right? So I want to put as much weight on the true label corresponded with that input. And basically, since it's a probability distribution, I can't just do that, I can't just put as much weight on that as possible. I have to take it away from the rest of the probability distribution, and that's what this is saying, right? So basically, explicitly take it from that particular mass of the distribution. Good. So you're going to see this kind of objective function in different forms. This is the conditional log likelihood. This thing here and different variants of it, whether it's, you push the negation into here inside the summation. These are often called things like log loss or cross entropy. They're loss functions that, it's the different name for the same thing, but they're loss functions that you'll see in neural network tools like PyTorch and things like that. When I get to the neural network section, I will cover that. But this is sort of the typical linear classifier representation of the problem. All right, so this objective is convex. I'll mention what that is in a second. So there's a single minimum, an optimum. There's only one that minimizes this objective function, which is good. So theoretically, we are, unlike the perceptron algorithm where we can find any hyperplane, that there's multiple hyperplanes that can separate the data if it's separable. Here we're just saying it doesn't even matter if it's separable. We care about this objective function, and there's a single minimum, and we're going to find it. And we can optimize that in a number of different ways. There's no closed form solution, but there are iterative solutions. And just as a side note, it's probably not relevant anymore, but about 20 years ago, maybe, people used to call logistic regression maximum entropy in natural language processing, and they're equivalent. But I don't think they call it that anymore. Okay, so what are convex functions? So basically, they're functions with a single global minimum, but also, because that's not enough, if you take any 2 points in that function, the line between those 2 points, the function is guaranteed that the minimum, the optimum of that function has to lie below that line, right? So there's a single optimization, the single point that optimizes the function. Okay, so how, so forgetting anything about natural language processing or things like that, just think abstractly in terms of functions. If we have a function that's convex, how do we find the parameters that minimize it? Well, this has been studied for ages, back to the time of Isaac Newton. The most common tool in our toolbox these days come from iterative descent methods, in particular gradient descents. And so the intuition here is that if you take any convex function and you take the gradient or the derivative at a point, that is the point where the direction is steepest towards the minimum, right? So we want to take a step in that direction. Now, we can't take a step too far. We actually want to take the largest step we can, but we can't take a step too far because in this case, if the gradient goes like this, right? If I take a step all the way here, then I might be up here. So I may have actually overshot the minimum. So we have this new parameter here. When we update the overall weight parameters, that is dynamically set, often with like a line search. You just sort of find it so that you always know that the objective function is going down. There's a lot of really nice heuristics for setting this as your training. But essentially, we want to, this new here represents how far in the direction of the gradient, right? The gradient with respect to that function, we're going to step in descent. And this is guaranteed. Basically, you can prove that if nu is set properly, so it's never set too big, eventually you're going to find, and it's greater than 0, eventually you're going to find the minimum of the function. You always just follow the gradient until you get to that minimum. I can't go, for time, I can't really go into any more details, but that's basically what we're going to use to optimize functions. But the main thing is, and I'm going to show you an example right now, as long as the function that we're optimizing is differentiable, it doesn't even have to be convex. We'll get to that in neural networks. As long as we can compute a gradient, we can always use gradient descent methods to find a solution. And that's basically machine learning in a nutshell today. Okay, so let's look at this in the specific case of logistic regression. So we're going to define this function L over the parameters and a particular input here. And we're going to call this our loss. So this is our per instance loss. And this is a value. A loss is a value that essentially we want to minimize, right? We want to minimize loss. In the perceptron case, you can think of errors as the loss that we want to minimize. We want to minimize the number of errors on the training data. In logistic regression, this is what we want to minimize. And we do that by maximizing the score of correct labels and minimizing the score of all the other labels, right? And like I said, this loss comes in different forms. People rewrite it in different ways. This is log loss or cross entropy, and neural networks is another way of referring to it. And so this would be our objective function to find the minimum of this loss for every single instance in the training data. So this is the maximum entropy, or sorry, I said nobody says it, but I just said it. This is the logistic regression optimization that we saw before. And the algorithm is quite simple. We again initialize at 0. We can initialize randomly because in this case it's a convex function, so we're always guaranteed to find the minimum. And then we just iteratively compute the gradient for either a single instance, in this case all the training instances at once. We just sum over the gradients of all the training instances, and we make a step in the direction. And we just keep doing that basically until some stopping criteria is met, which usually is that the value of the objective function, that loss, hasn't changed much, which is a sign that you're getting pretty close to the global optimum. It might just take too long to actually find the global optimum, so you just sort of wait until not much has changed. Good. We rarely use this form of gradient descent where we compute the gradient over the entire training data, which is just the sum of the gradients of every single instance. Instead, we often say like, well, okay, like perceptron, we're going to do an online algorithm, and we're just going to iterate. We're going to pick an instance, a single training instance, randomly or in order or whatever, and we're going to just make an update with respect to the gradient of that instance. And this has a lot of nice properties. First, if the data set's huge, it's a lot easier to compute because you don't have to kind of compute the gradient over a large training set. But there's actually a lot of empirical evidence that this converges a lot faster, actually significantly faster. And there's a lot of theory on ways to set nu so that you can also guarantee that you're going to find a global minimum. So it's a nice algorithm. And in machine learning, you'll hear a thing about in neural networks, you'll hear something about mini batches. This is kind of in between this online training where you have a single instance at a time versus what's called batch, where you sort of update over all instances. You just take a subset of the instances, like a much smaller subset, and that's your batch size. And modern architectures like GPUs and TPUs and things like that sort of are optimized for that particular paradigm. Okay, so we need to compute the gradient of this function here. So we essentially want the gradient of the loss, and once we compute that, we can just run gradient descent. I'm not actually going to go into the calculation. I'll let you look at the slides. It's a typical gradient derivative computation. There's a couple rules to remember, and here it is here. The key thing is the very last line, right? So what is the gradient of the loss function? Well, this essentially says that what I want to do is move in the direction where the expected value of features, so under the current model distribution, the expected value of those features is equal to the true value of the features, right? So this value will be 0 when I put all of the probability mass on the correct label, right? Because then basically I'm going to get a 1 when y prime equals y and 0 everywhere else, so that this will be 0, right? And this is kind of the intuition, getting back to maximum entropy. Basically, maximum entropy is a formulation where we say we want to minimize the entropy or maximize the entropy of the conditional distribution subject to that distribution's the expectation of that distribution's feature values being equal to the true feature values. And this is essentially the way to prove it. But that's the intuition for what the gradient means here. But either way, you can compute the gradient, plug it into your favorite, gradient-based optimization technique, and you will get a solution to the problem. Okay, so this is the summary of logistic regression. We define a conditional probability. We set weights to minimize the negative conditional log likelihood. We do that by predicting this gradient here, and then we just use gradient descent until we converge on some property. And that's logistic regression in a nutshell. So the story so far, on the top we have logistic regression, on the bottom we have perceptron. Just to show you that they're actually kind of similar algorithms, here is the gradient, and you can go back and sort of do the math and figure this out. This is the gradient descent update for logistic regression. We made this a positive and we swapped around the values here. We basically pushed the negative into the gradient. And this is the perceptron update. So you can see actually that these are quite similar. Whereas here we're just saying like, what we're moving mass towards is the same. What we're taking away mass is different. Here it's just the highest scoring label. Here it's everything, right? And that is primarily, once you actually get to the meat and potatoes of what gradient descent is doing, that is really the difference. Okay, so let me sort of prime you for the next half an hour, and then, after the break. And then after that, we'll spend the last hour on neural networks. So none of these really talk about this notion of maximizing the margin, which I'm sure a lot of you have heard about, right? So we did mention margin in the proof for perceptron conversion. So basically, the margin of a weight vector W is the smallest gamma, or the largest. Oh, it's the largest. I think that's a mistake. The largest gamma, such that that W scores or separates the true labels Y from incorrect labels by that margin, right? For every single training instance and for every single label. So that's the margin, gamma. optimizing for a margin kind of makes sense, right? So here's a training and a testing setup here. If it was perceptron, we could have found this hyperplane here, right? All perceptron guarantees you is that you're going to find some hyperplane that separates the data. However, once I get these new instances, they're in light blue. I don't know if you can actually tell the difference. We can see that, like, well, that wasn't such a great hyperplane after all. We're now classifying, what would we classify? 2 of these instances incorrectly in this particular case, right? So we would sort of say that, well, a better hyperplane would be as if we just rotated it a little bit, right? So that it was more kind of perpendicular to the points that are kind of closest to the decision boundary. And that's essentially geometrically what margin is, right? We're going to try to find not just any hyperplane, but the one that geometrically keeps the decision, the training data points as far away from that decision boundary as possible. And this makes sense, I think, conceptually, but also theoretically. So there still is, but certainly in the late 20th century and the first couple decades of the 21st century, a huge amount of work and conferences dedicated to proving results like this, that basically, generalization error is inverse to margin. So if I can find a classifier that has larger margin, I have better generalization error, lower generalization error, because I want to make less errors, essentially. And so right now we haven't really thought about that. The perceptron just gets a hyperplane, doesn't think about margin. Logistic regression, there's nothing encoded explicitly to maximize margin, but it turns out that it's actually doing something margin-y like. You can kind of, it's intuitive, right? If it's putting all its weight on the true instance and taking away weight from other labels, so the true label and from incorrect labels, that is kind of a margin-like optimization, even though it's not explicit in the optimization. And I'm going to loop back to that point later. So let me stop there, and we'll pick up with support vector machines after the break. Right, let me just kind of start by kind of taking stock of where we are. And I mentioned earlier that it's not necessarily super important to get all the details of the algorithms and the math and things like that. It's more important to sort of get the broad strokes of what we want to get out of this. And you can always go back and look at the slides that Andreas said. You can ask me questions to sort of get the details. So I would say, like, roughly here is the end-to-end picture of the lecture, right? So we have a text input, like the steak was cooked to perfection, and in sentiment classification as an example, we want to predict, okay, is it positive or negative, right? And the main concepts are all here, right? So on the input side, we have to take that text and convert it into something usable by the machine. So we've talked about sparse versus dense inputs. We've seen examples of sparse inputs. We are going to see examples of dense inputs. Feature engineering, we talked a lot about that. How do you sort of take a string and define features for this task? Word embeddings we're going to talk about. What are one-hot feature representations? These are other concepts for later. On the modeling side, we take that input and we push that into a model, right? And right now we've talked about linear classifiers. So perceptron logistic regression, we're about to talk about SVMs. But in that box as well as neural networks, right? The inputs get fed to the neural network. And theoretically, that boundary, that arrow there's no difference. They're all just real valued vectors that are getting pushed between boxes, essentially. And then on the output side, we have, is it a binary classification problem? Is it a multi-class classification problem? The latter of which we're talking about here. Do we transform that into probability distribution using a softmax, or do we just use the raw score itself? And also, what do we compute? Like when we have that output, we need some notion of computing a loss on it so that we can find parameter vectors. So log loss, conditional log likelihood, hinge loss is something we're going to talk about. These are the main concepts, and then we use that loss to basically that loss coupled with the model parameters to compute the gradient with respect to that loss, and we pass that gradient to gradient descent, some optimization tool. These are the kind of the main concepts, and we've already covered little bits and pieces in here. Like, so, for logistic regression, how do you actually compute that gradient? We did it analytically, and we'll see in neural networks as we'll look at backpropagation. Okay, so keep this in mind when I'm going through the lecture, especially if there's like some small detail that is troubling you, you can probably get back to it. All right. Okay, so this is the last little bit of linear classifiers. Okay. So if you remember, just before the end of the break, we talked about this notion of margin, that, right, all else being equal, we want to find decision boundaries that optimize margin. That means the instances in the training data should be as far away as possible from that decision boundary. And there's theoretical and also intuitive reasons for why we care about that. So let's actually look at explicitly maximizing the margin, right? So here is an optimization here where we say, okay, so the margin is gamma. We say, okay, maximize the margin, subject to some constraints. These constraints down here say the score of the correct output yt for input xt has to be greater than the score of some other output y prime not equal to yt, and it has to be greater than that margin, right? So we're essentially saying, getting away from the geometric view and looking more at the arithmetic view, we're saying that this is what we mean by margin, that we are classifying instances, the correct instance and the incorrect instance, and the gap between the scores is the margin. We want that to be as large as possible, and we want that for every single training point and for all the incorrect labels for those training points, right? This still minimizes error. If we can actually optimize this function perfectly, then we're going to get zero error. We're going to perfectly classify our training data. There is something here which is going to be important, is we actually bound the norm of the weight vector to be 1. And the reason to do it here is simply I can always, take a different weight vector with the larger norm, just scale the weight vector up and get a larger margin, right? So it's kind of vacuous to maximize margin without having this particular constraint here. So that's kind of the explicitly, let's maximize margin optimization. In practice, we actually talk about minimizing norm, the norm of the weight vector, and they're equivalent. So on the left here is that optimization I just showed you before, where we're maximizing margin. On the right here, we have an equivalent optimization where we are minimizing the norm of the weight vector, but instead of fixing the norm of the weight vector to be 1, we instead fix the margin to be 1, right? So we want the smallest weight vector as possible so that we can correctly classify all the training instances with a margin 1. And that's, for all the training instances, for all the incorrect labels. And to see why that is the case, this bottom line, why these are equivalent, this bottom line here shows you why. I can just reparameterize and say, oh, w prime equals w here over the margin. I solve for the margin, and I have, and I take the norm, and since the margin is a scalar, it's the same. I have the norm of w over the norm of the reparameterized one, which is equal to the 1 over the reparameterized one. So maximizing this margin is equivalent to minimizing this norm. So that's the intuition. And this is support vector machines in a nutshell. This is what we optimize with support vector machines, right? We minimize the norm. This half here and the fact that we square the norm is purely a mathematical convenience to make the derivatives easier. They don't actually change the solution or anything like that. But yeah, and so this optimization here, right, is a quadratic programming problem because we have a quadratic objective function with linear constraints. This has actually been studied, how to optimize these functions there's a huge amount of literature on it. However, it's a pretty heavy mechanism, the tools out there for doing that. So we're going to rewrite this a little bit and introduce some variables so we can get back to optimizing it through gradient-based techniques. Okay, and this kind of gets to a point earlier. What if the data is not separable, right? What if I can't actually find a solution to this problem? So here is a version of support vector machines with what's called slack variables. So these xi here, these variables are called slack variables. And essentially, they allow you to trade off how important it is to classify some instances correctly with a good margin versus maybe make a mistake on some other instances. So we say now we're minimizing over the parameter vector W and the set of slack variables. So there's one slack variable for every single instance, right? And basically, if I can set all those slack variables to 0, then that's great. That means, and I can optimize this, then that's great. That means I can actually find a separating hyperparameter and I can get 0 error. However, the slack variables allow you some flexibility to maybe not separate this instance by a margin of 1, right? So maybe, you know, you can think the classifications are dependent, right? Maybe by not classifying one instance with a margin of 1, I allow my parameters to classify 10 more instances with a margin of 1. So there's a bit of a trade-off happening here, and the slack variables give the model flexibility to do that. And then there's this hyperparameter C that basically says how much do you want to sort of minimize error versus trade off that flexibility, you know, with margin. And that's a hyperparameter. You don't learn that. That's kind of something you set, and it's usually set empirically. So this is, in practice, this is people use slack variables with support vector machines. Okay, so let me rewrite this a little bit, and this is the part where the details aren't super important. You can go back and look at it. First, instead of using C, I'm going to use lambda. I'm going to multiply the objective by 1 over C, and I'm going to call that lambda just to move this over here. Down here, this is exactly as before, the same objective, the same set of linear constraints as before. Right. So let me say, so basically what to notice here is in this optimization, I'm saying that this has to be satisfied for every single incorrect value, right? So y prime comes from, you know, for all y primes in the set that aren't equal to the true value. What I'm going to do is reparameterize that, not reparameterize, just rewrite that and say, well, it's equivalent if I say this is true for the y prime that has the maximum score, right? So if that's true for the y prime that has the maximum score, not equal to yt, then it has to be true for all the other labels as well, right? That's just the case. So this is equivalent here. This is just rewriting, moving things around on the inequality. Okay, and so this is kind of the key point here, right? So if the way to sort of conceptually think of this optimization is that if the parameter vector W classifies this particular training instance with a margin 1, then you pay no penalty, right? You basically can set CT to 0, and I don't pay any penalty in my objective function. Since I'm minimizing this, you know, you can think of penalty as any time that I'm increasing this value, right? So keeping all the C's of T's 0, because they have to be greater than or equal to 0, you don't incur a penalty. Otherwise, the penalty is going to be exactly this value, 1 plus the maximum incorrect score minus the true score. And to see why that's the case, I mean, in this objective function, it wouldn't make sense to have C of t greater than this value. It has to be greater than or equal to according to this linear constraint here. But you wouldn't make it any greater because in the objective function here, you would pay a penalty, right? So it's going to be exactly equal to that, to the right-hand side of that inequality. And this is hinge loss. So we talked about log loss before. But this formulation of support vector machines is a hinge loss formalization. So the loss here for a particular instance is the maximum of either 0 or this penalty here, the C of t, right? So essentially, this is what I want to minimize for an instance. I want the parameter vector W to minimize this. Ideally, I separate it separates all the training instances, and the penalties I pay are 0. But otherwise, if it can't do it, I want the C's of T's to be as low as possible, right? So this is where hinge loss comes from. And hinge loss, when people talk about it, all they're talking about is margin, you know, maximizing margin relative to some fixed margin. Okay, so the top is the original sort of quadratic programming version of support vector machines with a slack variable, and below is the typical way that we write them, right? So we have an objective function. We want to minimize the parameter vector W, sum over all the training instances, the loss of those training instances. So this is identical to logistic regression. Here, there's a little caveat. We haven't really talked a huge about this minimizing norm term. We're going to leave it here. I'm going to get back to this in a second. This is kind of an interesting point here. But this is our objective function. And the loss here is hinge loss. Okay? So this is support vector machines. That was quick, so I want to make sure people follow. But I mean, the key thing here, like always, getting back to that first slide of the lecture, is not the details. How do you derive the hinge loss? You can go back to the slides and see that for yourself. The key thing is that support vector machines, are exactly the same as logistic regression. We are minimizing some objective function where we have a loss. Unlike logistic regression, where that loss is log loss, here this loss is hinge loss, right? Which is enforcing, and you can think that, well, hinge loss is enforcing a margin in the classification. And this is differentiable. It requires something called subgradient descent because at various points in the objective function, there's not a single gradient, there's multiple gradients. I'm not going to get into the details. I'll point you to some slides that do, but we just use gradient-based techniques to solve this anyways. That's kind of neither here nor there. Okay, so now I'm going to talk, so that's support vector machines, that's it. You learned them in 11 minutes. 30 years of research, there you go. But I'm going to talk now a little bit about what this term means and tie this objective function into logistic regression and perceptron algorithms. And then I'm going to be done with linear classifiers and we can move on to neural networks. So what we've covered, logistic regression, perceptron, support vector machines, regularization, and nonlinear classifiers. Okay, so I haven't talked about this at all, but there's this concept of overfitting, right? So let's say this is my data. I want a function that fits this, this data so I can make predictions, right? Essentially, we have these h, the classifier is a function h, and it comes from some set of potential classifiers, functions. By selecting the parameters w, we are selecting one of those h's, right? That space has some capacity, like it's linear, it's nonlinear. There's some kind of capacity to that space, and we essentially want to control that capacity, right? We don't want to control it too much, right? So this is actually an example. Well, the data is not linear, and a linear classifier doesn't really do a good job at fitting the data, right? We probably want a function like this, so it's called balance in this slide, but basically we want a function that looks like it's really explaining the data and nothing more, right? That the data looks like it's quadratic here. That seems like a good, we'll use a quadratic function or something like that. This is called overfitting. So this is when I make the space of functions, classification functions that I'm selecting from way too rich, right? So here this would be like some polynomial function to a high degree, and basically it explains every single point exactly. It's just like a function that jumps from point to point to point. And this is not particularly useful because when I get a new point that I haven't seen before, the odds that it lies somewhere on this curve are extremely unlikely. So we want to sort of balance off overfitting, which can happen when we minimize error on the training data, because we can basically, if that is our objective, we don't really care about generalization, versus underfitting. We want the model to have some power as well. We'd like to be in this situation. So basically, since the objective functions we're looking at, these loss functions, tend to minimize error, something like minimizing error, they tend to overfit as well, right? They tend to do really well on the training data, but then once you give them new instances, the accuracy drops off a cliff. And that's, a standard thing in machine learning and natural language processing. So what we want to do then is not necessarily, change the classifier or change the feature representations. We want to sort of control the capacity of that classifier itself. And there's lots of ways of doing that, and I can't go into all of them. But the two most popular ways, and this is through a regularization term. So essentially, we have our normal objective function here. We want to minimize loss. And then we say, okay, subject to some regularization, some function on those parameters that controls its capacity. And the two most common ones are, they come from Bayesian literature, a Gaussian prior or a Laplacian prior, often known as L2 or L1, because they manifest themselves in terms of the L2 norm or the L1 norm. And intuitively, basically, the Gaussian prior wants a classifier that has low error on the training data, but it wants to keep the weights as small as possible, right? So, don't put massive weights that over-explain certain examples. As long as you can sort of minimize error or likelihood or whatever it is, the smaller the weights you can do, the better. And this lambda here controls how much you want to sort of control the capacity of the model versus control training error rate. So this is empirical risk minimization, that sort of trade-off. And L1 is quite popular. It promotes sparse weights. Basically, I'm not going to sort of go into that, but usually what happens is this zeroes out a lot of weights. So most weights are going to be 0 if lambda is particularly high in this instance. So the intuition here is that I want a classifier that has high accuracy or low error on the training data, but I want to use the least amount of weights possible to explain that. Okay, so how does that change the linear classifiers we've looked at so far? So logistic regression with an L2 regularization. This is like perceptron, probably, I would say perceptron, logistic regression with an L2 regularizer, and SVMs accounted for 95% of classifiers in NLP over the past 20 years until neural networks. So we simply add on this regularizer term, which we set to the L2 norm. Nothing really changes. We already derived the loss, the gradient of the loss for logistic regression. The gradient of the regularizer is simply equal to lambda times W. And so when we're doing gradient-based optimization, we just add that to the gradient, and you're done, and you're doing L2 regularization. Okay, support vector machines. Actually, it turns out that L2 regularization is already happening, right? If this is linear classifiers with a regularization term, then we expand that to hinge loss and a regularization term, and we say, okay, well, this is a L2 regularization. I mean, there's some constant scalar that's being multiplied, but that's not really changing the solution. So you can think of SVMs essentially as hinge loss with L2 regularizations. That is SVMs. And all of the theory before that, that's what it boils down to. So, let's look at the differences between SVMs and logistic regression, right? They both take the same form. There's a loss function and a regularizer. The regularizers are essentially identical. What's different is whether we use hinge loss or whether we use something like log loss. So I rewrote it a little bit to maybe make it a bit more intuitive. But basically, hinge loss is saying minimize the number of misclassifications I make relative to a margin, right? So you do well on hinge loss when you classify correct instances higher than incorrect instances subject to some margin. One, if you rewrite the log loss of logistic regression, you basically say okay, well, now I'm minimizing an objective function with a probability of incorrect labels, really the entire label set, has to be low, and the probability of the correct label has to be high, right? So these are very, very similar optimization functions. They do tend to get different solutions, but they're really not that different from each other. And this actually, in the literature, when you look at papers from 2010, the difference between using something like SVMs versus using something like logistic regression is usually marginal. There's rarely a difference in accuracy. And that's actually true for perceptron as well, right? We can say, again, looking at SVMs versus perceptron, this is the SVM optimization up top, where we say, okay, there's this margin of 1, and there's this regularization term. Perceptron, we can say, is actually a hinge loss as well. It's basically like an SVM. There's no margin. We're not enforcing a margin at all. We drop the 1 term. And there's no regularization term either. So that's the main difference. So all of these linear classifiers, almost any linear classifier in the literature that you find, in particular conditional or discriminative linear classifiers, you can write in this way, and they only change in one of these ways. Do we have a regularization term? What is that regularization term? And what does the loss look like? So this is kind of a critical point with linear classifiers, and generally classifiers, right? We often parameterize them the same way, and the thing that makes them different is how we measure loss, and then that influences what the gradient looks like when we're optimizing these functions.
I wanted to ask something about the bias variance trade-off.
Yeah.
Because it's very, it has to do something with the regularization, and I've always struggled to find out what the high variance actually means, because in some literatures I just read that high variance means high variation in predicted values, and somewhere I just see that it's high variation in our parameter values.
Yeah.
So, and how does the regularization help us? I mean, I know how it does. It doesn't let us just making parameters too high, like too so exploding values, so our model will be overfitted. But maybe can you just say something a bit more about the bias variance trade-off?
Yeah, sure. I mean, like you said, the last statement you made is, I think, the biggest intuition, right? Like, it basically doesn't allow us to, you know, put a lot of weight on, let's say, a single feature that just happens to be predictive for an instance or a set of instances in the training data. But usually when we talk about variance in this setting, we're talking about on the parameters themselves, right? So we have, like, this is why it's a Gaussian prior. There's some distribution that the parameters come from, and that is constrained in some way, right? So it's, we're you know, based on how we set lambda, or how we set the Gaussian distribution that we're drawing those priors from, we are constraining the variance of the parameters that we can select from. When you talk about variance on predictions, and this is, I'm going into a space that I'm not an expert on, there's certainly been a lot of work on stability, right? So, like, trying to understand for these classifiers, which, you know, how do you control for stability of predictions on some unseen data set, right? And there's some learning theory called, you know, called stability bounds that show that, like, when you keep the variance of that low, you get high generalization error as well. So if I understood your question correctly, both exist. We're talking specifically about variance in the parameter space, but definitely in the learning theory space, people do talk about variance on the prediction space.
Okay, thank you.
Does that help?
Yeah.
Okay. We can talk more offline as well.
Yeah, thank you.
So actually that gets me to this point here. We're done linear classifiers. You know, we'll see, they'll come up again in neural networks. Andre Martin gave a similar lecture, and actually I based a lot of this lecture on some of his slides. And he, because of timing, he was able to speak about other linear classifiers like naive Bayes. Also subgradient descent techniques, I mentioned that quite briefly, but also non-neural network models that are, sorry, non-linear models that are not neural networks, which was a very important topic of research up until about, I would say, 5 or 6 years ago. And this includes things like k-nearest neighbors, which I have to say are making a comeback. You know, so that could be something to take a look at. It's a bit more of an advanced, their comeback is a bit more of an advanced topic. And kernel methods, especially with respect to support vector machines, was very popular for a while. So, okay, let me go back to the beginning. If you remember, we said, okay, this is a linear classifier, where we basically take some input, which would be a document or an image, if you cared about computer vision problems, and you handcraft some features, right? You say, like, okay, well, you know, like whether a word occurs in a document, or what is the suffix of a word, these sorts of features are useful for making various predictions. Those handcrafted features take your input, it maps it to some high-dimensional feature representation, and then we pass that to a linear classifier, which makes a decision. Right, so a bit of a notational switch here. Before, I was using the joint feature map for inputs and outputs. It's kind of historical. It's very common in linear classifiers, and it actually makes talking about some of the methods a bit easier notationally. I'm going to switch to the feature representation only over inputs now. And you remember they're equivalent, so nothing under the hood is really happening here. It's more notational. And I'm specifically going to use this representation where we say, okay, our features map to some high dimensional space, dimension D. We have a bunch of weight vectors, also of dimension D. Each weight vector is per class, right? So instead of having this block feature representation, I'm going to have a much smaller feature representation, which just fires features for the particular input. And then for every single output label, output class, I have a set of parameters that scores those features. And I'm also going to introduce the bias term, again, which is just a linear, just a scalar. But the output of this here is a vector, right, where the vector is the value for every label or every position under these parameters, right? So the value of the first position of the vector would be the score of label 0, the first label, etc. And our prediction is just the argmax over those vectors, right? So I'm also going to do another notational shift, and I'm going to say, well, we don't even have this feature mapping at all, right? We're not going to hand design features anymore. Our inputs are just X. We just have high dimensional representations of the inputs themselves. And you'll see why that's convenient and natural to do in this setting, right? So I basically have, my input now is a high dimensional feature representation, so that can be a document, a word, whatever it might be, and then I just do this linear transformation. Okay, neural networks. So we're primarily going to focus on feed-forward neural networks in this lecture, and a lot of the other lectures are going to focus on more advanced topics. But this is a feed-forward neural network. It's often called a multi-layer perceptron. It goes by a number of different names. Basically, in its most generic form, what we have is an input layer. So this is the same as before. We have some inputs, or documents, or a sentence, and we represent that by some high-dimensional vector. We then have these hidden layers. So these are, again, vectors. So we take that input, or we take another hidden layer, and we basically transform that representation into another vector, right? So we're projecting, and these are nonlinear projections from one vector to another. These values here are often called neurons. Sometimes we just say the ith dimension of this vector. It's ultimately a vector. Neuron comes from the early literature where these models were sort of influenced by neurology. And then we have an output layer as well. And these lines here are layer connections. These lines are the parameters of the model. These are the weights that connect different layers together, right? And so if we got rid of all these hidden layers, that would be a linear classifier. We're back to linear classifiers. And usually, almost always, I would say, we assume that the layers are dense, and that means that at this layer, any neuron is connected to all the neurons of the previous layer. So at any given layer, a neuron is a function of all the neurons at the previous layer. And that's what it means to be dense. And I'll talk a little bit about neural network structure in a bit. Okay, so most of the action happens at the input and the output, right? So let me start with the simple part. Hidden layer to hidden layer, right? So we have these deep neural networks. This is just an example where I have 2 hidden layers. If I had no hidden layers, it'd be a linear classifier, but this has 2. So let's look at the part of the neural network that goes from one hidden layer to another, right? So a hidden layer we're going to say is H, bold H. I is the ith hidden layer, and we'll say it has dimension D to the subscript of I, and that means that it has di neurons, that layer. It's just a vector. And in feed-forward neural networks, multi-layer perceptrons, the value of the ith layer, so this is not the index, which actually I should have made clear in the notation, so I apologize for that. This I doesn't represent the ith position in the vector. This I represents the ith layer. So h of I is still a vector itself. This is equal to a affine transformation, so a linear transformation over the previous layer, so hi minus 1, right, with some a parameter vector, parameter matrix W and a bias vector B, as well as a nonlinear component-wise operation, not necessarily nonlinear, an activation function, component-wise function that operates over every single neuron in this vector. A useful concept, and you'll hear this a lot, is this idea of a logit, which is essentially the scalar value here, the raw values through the affine transformation before they've been put through any sort of activation function or things like that. And so just to make it clear, you know, Wi is a matrix of di times di minus 1 projection. So your projection from the previous layer's dimension to the current layer's dimension. The bias term is of dimension I, right? So the new layer is going to have I, d of I values, right? It's going to be a vector. And f of I is the layer's activation function. All right, so activation functions, what are they? They're typically nonlinear and they're typically squashing functions. And there's a lot of reasons to have these functions, most of which is by squashing the parameter vectors into a discrete space. Often it makes the gradients easier to compute. I should, not analytically, it doesn't make them any more analytically easier to compute, but it makes them more stable and it makes the gradient optimization work better. This is more of an empirical observation than a theoretical one. There are a ton of activation functions, and there's a whole field of study in neural networks on looking at different activation functions and how you even learn activation functions, right? Making that part of the network that you learn as opposed to just a function I pick off the shelf. But I would say in NLP, the most common ones are sigmoids, which squash the values on a range from 0 to 1, the hyperbolic tangent, which squash the values on a range from -1 to 1, and a very popular one is the rectified linear unit, which basically says if the value is less than 0, make it 0, otherwise just return the value itself. And there's a lot of variants of this particular one as well, and there are even some arguments in the literature that this is actually how neurons in our brain behave, but you know, I think take that with a pinch of salt. Okay. So that is what a hidden layer looks like. It's essentially a linear transformation from one vector to another of potentially different dimensions, followed by a component-wise squashing function that squashes all of those neuron values into some range. Unless it's a rectified linear unit, which it doesn't squash, it just transforms them. Okay, so that's the hidden layer. Any questions there? Okay. Let's look at the output, the output layer, so the very last layer of a neural network. And we actually don't have to talk about this a huge amount because we just spent the past 2 hours talking about this. These are linear classifiers. We take the final layer, instead of those being handcrafted features, it's just the last hidden layer. We pass it through a linear transformation and we take a loss, right? And almost always that's going to be a hinge loss or a log loss. In neural networks, people tend to say cross entropy instead of log loss, but they're identical. So if you're using PyTorch or TensorFlow and the loss function says cross entropy, it's log loss. It's exactly what we talked about today. Right, so I'm actually not going to spend a huge amount of time there because that's, I think, hopefully we've covered that. Okay, so before I talk about the input layer, and the input layer is, as usual, the most interesting part, let's just take a look at a little example. And I hope this is readable. Is it? Yes. Okay. So let me just, this is a very toy example. We have an input of dimension 2. We have one hidden layer of dimension 3, and our activation function is going to be a hyperbolic tangent, right? And by setting those, what are called hyperparameters, setting the dimensions of the inputs and the hidden dimensions, as well as the number of outputs, which is task specific, that dictates the shape of our parameters, right? Like our matrix that maps from inputs to outputs has to be 3 by 2 with a bias of dimension 3 because we have 3 outputs, and similarly going back to 2 outputs on the output layer. And actually I wanted to make explicit here that these edges that you see drawn in neural networks. We often see neural networks drawn with neurons and then a bunch of different edges between neurons. Essentially what those edges represent is that linear transformation and activation function, and then the output is the value of the neuron. So it's not like we're just passing the value over, or that we're just summing the values. We are, well, I guess we are just summing the values in this case. We are doing that computation, the layer-to-layer computation, and that's where that happens. And then on the output layer, we predict a score, right? So these are scalars. If we're doing something like hinge loss or perceptron loss, that's it. We can compute the loss on the raw score itself. If we want to do something like cross entropy or log loss, we pass this through a softmax layer. So this is extremely common in NLP literature. And then that gives us a probability distribution, so then we compute log loss in that way. Okay, so neural networks so far. Again, we're just looking at feed-forward, dense, multi-layer perceptron networks. The input, now we're just going to assume is given to us. Magically, someone said, here is a real valued vector for your input. We have some outputs that's task-specific. If you're doing sentiment classification, it's positive or negative. And then we have a bunch of hidden layers, right? And those hidden layers are defined by the parameters for those layers themselves, which in this case is a matrix, W, a bias vector, B, and an activation function specific to that layer. And then, of course, we have to define a loss function. Like linear classifiers, we make some prediction, we incur some loss during training, and that guides the gradient computation backwards. All right, so that's in a nutshell before sort of getting into what the input layer looks like. These models are nonlinear because of their transformations. Basically, the way we talked about earlier, XOR, we can transform the input, project it to a different space so that we can do a linear classifier. That's essentially what neural networks are doing. These hidden layers are transforming the input into some, projecting it to some different space. Now, it's just doing it in a latent way. It's being learned as part of the objective function as opposed to a human sitting down and saying, here's how I want to project that input to a different space. It's just happening as part of the optimization. These hidden layers do come with a caveat, is that the model's no longer convex. So there's no single global minimum for this objective function. And you can test this out by just having taking this particular network, computing some derivatives, and checking that the second derivative is not always greater than 0. I think that's the definition of convexity. Anyways, but they're differentiable. And I think for many years people worried about that a lot, right? Basically, you're not guaranteed to get the global minimum. You're going to get some local minimum, right? You have this non-convex function that has many bumps, many local optimas, and we're making no guarantees. We're going to get one of them, but that can actually be very, very far from actually the global one, right? And people did worry about that a lot. It turns out in practice, it's not really that big a deal. But that's an empirical statement, not a theoretical one. So the key, again, is that as long as in this neural network, all the operations that we have, like the loss functions that we compute, the transformations between layers, the activation functions that we decide on, as long as all of those are differentiable, we can always compute a gradient. We take a loss at the end of the network, a log loss, a hinge loss, and then we can always compute the gradient with respect to that loss as long as all the operations are differentiable. And then we can do gradient descent and stochastic gradient descent. Yeah. Okay, so, right, if we can compute a gradient, that's great. We can do gradient descent, stochastic gradient descent, things like that. However, the bigger these networks get, right? So, one of the main advantages of neural networks is we can have these huge, deep networks with lots of layers. Computing the gradient becomes a little cumbersome, in particular, computing it analytically. And so this is where backpropagation comes in. It's a very old algorithm from the 80s, I think 1986 or 87. Right, so we say, okay, the gradient is essentially the partial, with respect to a loss function, is the partial derivatives of that loss function with respect to all the parameters of the model, right? What we're going to use is the chain rule, which is a well-established rule that says the gradient of a function z with respect to a parameter x is equal to the gradient of a function z with respect to perhaps another function y times by the gradient or the derivative of function y with respect to parameter x. And from a neural network standpoint, what that means is, let's say I have a loss function L, and I want to compute the partial derivative of x with respect to L, right? What I need to know in order to do that is the next layer up, the partial derivative of L with respect to z. And if I've computed that, then computing the derivative of x with respect to z is easy, right? This is usually, every layer is usually just a linear transformation plus some activation function, right? So that's not really hard to analytically compute that particular gradient. And that's all you need to do at every single layer, as long as you compute, that simple gradient there. Then I can rely on the chain rule to assume that if I've computed the gradient one layer up, I can just multiply that by the gradient at this particular layer, and everything is good. Okay, so let me kind of maybe get too detailed. I'm not sure. So this is actually not a fully dense network. It's just a little toy example where we have 4 inputs, and it's not dense. So basically, we have 2 hidden layers. Hidden layer 1 is basically a linear transformation, no activation function between weights W1 and W2 and the 2 input layers, and hidden layer 2 the same. So these nodes in purple are the actual model parameters. Usually when we draw neural networks, the model parameters are sort of like implied by the edges between neurons in the network. Here I'm just kind of explicitly pointing them out, making them nodes as well in the graph, right? And so everything else is fixed. We're going to assume that the inputs are fixed. The hidden layers are not fixed, but they're just computed from lower layers as well as the output. So what we need to do, the model parameters, are essentially these 2 u's that create our output y as well as the w's. So these are the partial derivatives that we need in order to compute the gradient. These are the layer-wise derivatives, right? So what is the derivative between layers? So the derivative of derivative of H1, node hidden neuron, H1 with respect to W1 is equal to X1, right? Because basically that's 0, and then, that derivative just becomes X1. So these are all the layer-to-layer derivatives. So in order to compute, and then the loss function here, this is called just a squared loss. We're going to assume the output here, just for simplicity, is just a real value, like some scalar. And the loss we're going to take is essentially the difference between the scalar that we predict and the true scalar. And we square that to make sure that it's always positive. So we can analytically, this is a small network, we can say like, okay, well, the derivative of U1 with respect to L is easy. I use the chain rule, and then I multiply out, I pull from this table, and I multiply things out. Similarly, the derivative with respect to W1, I use the chain rule twice, because I have to go twice down the network. I pull those values out from this table, and I have my derivatives, and I do that for all my parameters, and I get my gradient. But again, that works nicely because the network is shallow. There's only one hidden layer, and there's not many neurons, right? So either writing that out by hand for all the different layers is certainly not something you'd ever want to do, but also computing it, there's a lot to sort of, a lot of bookkeeping that has to happen. And so this is where backpropagation helps, right? Essentially, the reason it's called backpropagation is for any example, I take some inputs, right? So here now I take a particular x value, which is 2, 4, negative 5, 3, and I know this is training, so let's say my true y value is 1, right? And then at some point in time, my parameters are set to values, right? So this is during some point during training, I have a certain set of parameters I've learned so far, and maybe they're just randomly initialized at the start. And so I basically run all the way forward through the network, and I compute the value of y, right? In this case, the value of y is negative 1. So this is my forward pass in backpropagation. And then what you start doing is passing gradients backwards, right? And this makes the computation, at least the bookkeeping, easier when implementing, because you just have to keep, the forward pass determines what's called a computation graph, and then as you come backwards in every node in that computation graph, you just pass the gradient from the last node. So here, we don't have to expand the chain rule beyond one layer in the network. So before, when we had to compute the derivative of the likelihood with respect to W1, we had to use the chain rule twice, right? Here now, we just use once, right? Derivative with respect to H1 and H1 W1. And since I am coming backwards in the network when computing this, by the time I need to compute the derivative with respect to W1, I've already computed the derivative with respect to H1, so I can just look that up, get that value, and multiply it out. So this is backpropagation in a nutshell. I'm not going to go through the example here, but this is kind of a fully, it's a two-layer network with 4 input values, so it's not a lot, but these things get pretty hairy quickly. But you can follow this example all the way through, compute the loss, and compute the gradient all the way back. And this is how you would compute the gradient for this network in backpropagation. Okay? Again, the details of backpropagation are not critical to sort of nail down right now. The key is that it's a tool to compute a gradient in a neural network. And it's essentially a tool that makes it computationally convenient to compute that gradient. All right, let's talk about the input layer. So I have half an hour left, which is good because the input layer is, I think, probably the most interesting part of this. Okay, so we said that we're going to assume for a while that we just know the input. Someone has magically given us a real valued vector x, for an input x, right, of dimension d. So what is this for language? Words are discrete. Obviously, we don't just get this for free. If you think about something like image processing, it kind of does come for free, right? You have an image, it has pixels. Those pixels have RGB values. You can kind of say, okay, well, I'm just going to linearize that into a vector, and I have a real valued vector of the image. That's a little naive. That's not what people do in image processing, but at least, naturally, it's a dense real valued vector, where in language, naturally, it's just not, right? We have discrete vocabularies, and we have to convert that to something dense. So we could say, well, okay, mathematically or theoretically, there's no reason we can't just use these sparse representations that we used in linear classifiers, right? And actually, theoretically, there's no reason we can't use dense representations in linear classifiers either, and people do. I should point that out. But by using sparse representations, there's a couple issues. First, the number of parameters grows quite dramatically. So you get sparsity, and the more parameters you have, the bigger the class of models you're searching from, so you get things like overfitting. And there's also implementational details, right? If you have this huge sparse vector that's the size of your vocabulary, and in English, there's millions of words, that first layer is going to be like 1,000,000 times the output of the hidden space matrix computation, which is not necessarily the most efficient computation out there. So the solution is like, well, let's just embrace the vector and represent words or text directly as real valued vectors. Okay, so let's consider classifying. So now, just to make things simple, forget documents, forget sentences. Let's just focus on words, right? And one very sort of artificial case is I'm given a word in isolation, and I want you to tell me, is it a verb or a noun? Obviously, this is contrived. I can never tell work whether it's a verb or a noun without any context, because it can be both. But let's say that's the task ahead of me. So my goal here is I want to create a dense representation for every single word in the vocabulary. And let's call that vocabulary V. And it's finite. Even though new words are being created every day, let's assume that we have a fixed point in time. There's a set of words, and we want to learn a representation for every single word in that vocabulary. So this is often called the embedding layer. Word embeddings, things like this. You've probably heard that term a lot. It also goes by lookup table, because from the input, you look up the vector of a word from this table. Graphically, this is it. This is a matrix where every single row, it's the number of rows is equal to the size of the vocabulary, and every single row is the dense representation for that word, right? So if we can learn this, and we want to classify words into some categories, well, we just have to look up that representation for the word, right? So we have some hash table that maps from a string word to some index in this lookup table. We take that vector out, and that's the input to our neural network. Okay? So there's lots of views on this. One is to say, well, that table is static, right? So it's not trained as part of how we train the rest of the neural network. So it's kind of fixed. We've either given to us or we've learned it through some other process offline. And there's a lot of examples of this. I'm going to go through Word2Vec, which is a very popular instance, but there's others if you're interested. Another view is that they're dynamic. They're part of what the neural network actually learns itself. And I'll show you how that's possible. But basically, that lookup table, these are just parameters in the model. And backpropagation, we're going to randomly initialize this table. And backpropagation is going to update the parameters in this table as well. So we're learning the word representations, not in some offline setting, but specific to the classification task that we care about. And then, of course, we can combine them, and there's generally two ways of doing that. Probably the first way is the most popular. We learn some word representations offline using a huge amount of data through something called unsupervised learning, and this is what Word2Vec does. And then when we want to train a neural network classifier, we essentially initialize the values of this table with our pre-trained word embeddings, but then we allow the classifier to fine-tune them, is often what people say, to fine-tune these embeddings to improve classification accuracy. So you have sort of a generic offline representation of words that you then fine-tune through backpropagation specific to your task. And this is kind of a very important notion, not super important for this lecture, but I think lectures 3, 4, and 5, this is going to come up. Things like Elmo, BERT, XLNet, these are all examples of this, but using different neural architectures. The static dynamic case. So let's look at an example of generating some static word embeddings, right? So the goal here is we just want to learn this table, and then we're going to fix it, and we're going to feed that to the neural network. Okay, so there's a lot of detail here. Again, don't worry about the finer points. I'll point out the main things that you want to take home from here. But okay, so we have a corpus C. So this is a huge collection of documents with sentences. And the nice thing about this is this can be any corpus. We don't require any labels on this corpus, right? So you can take a web crawl or take like a bunch of news articles or whatever. There's a lot of corpora of documents around, and we split those into sentences, and that's the input to this method. We have a vocabulary, which we essentially derive from that corpus, right? So every single word that occurs in that corpus is in our vocabulary, right? So it's finite. Word2Vec specifically defines 2 embeddings per word. We're going to say bold X of I represents the word itself. So this is the word embedding we care about, right? This is what we're going to learn. But we also have this sort of parallel one, which represents that word in context, right? So, and I'll show you what that means in a second, but we're going to learn what it means for a word to be sort of the focus and what it means for a word to be some context of another word's focus. Right, so Word2Vec optimizes this function here. Just quite briefly, basically what it says is for every single document in the corpus, for every single sentence in those documents, for every single sentence in the corpus, for every single word in the sentence, I want to maximize the probability of seeing a word in context given some word at position j. So given a particular word, I take the sentence and I look at its context. And here context is these offsets k. So that might be, if k is 1, it's the word to the right of me. If k is -1, it's the word to the left. And this parameter c controls how much of that context you actually want to look at, right? And I want to maximize that. So essentially, I want some word embeddings where I represent a word so that it can predict which words typically occur around it. And this sort of intuition has a very, very long tradition in natural language processing. And it's probably, I would say, the starting point of natural language processing, that particular intuition. So the way they parameterized this was in a log linear model, a softmax. We say, okay, the score of a word predicting its neighbor is a linear dot product. So the representation of the word and the representation of its neighbor, but the contextualized version of its neighbor should be high. And that, make that a probability. Essentially, if we think about optimization, what this means is that what I want to do is put as much probability on predicting my neighbors and take away probability of predicting all the other options, all the other words in the vocabulary. So maybe to make this a little bit more clear, here's an example. So we have the quick brown fox jumps over the lazy dog. So let's focus on the word brown, and let's say the context is 2. So 2 words to the left, 2 words to the right. What we want the model to be able to do is predict with high probability that the, quick, fox, and jumps occur around it, not in any particular position, in this particular incarnation of the model, and that all other words it predicts with low probability. Of course, brown is going to occur in a lot of other contexts, so that's not necessarily the best objective function, but it turns out that in practice it's pretty reasonable. And one way you can use this particular example is to say, like, well, I can then generate a large number of training samples, positive training samples from an unlabeled corpus, right? If I sort of move a sliding window along this sentence with context of size 2, I can say, like, okay, here are examples where I have a word in focus, so that's the left word in this pair, and I have some contextual word. And these are my positive training examples. These are the training examples I'm going to use to optimize this objective function. Okay, so I'm going to rewrite this equation a little bit. I'm not going to go into the details. It's just simple rewriting. But we can rewrite this in a way that says, okay, well, actually what I want to maximize is my ability to predict my words in context, the words that actually occur in context for a given focus word. That's this term here. And I want to minimize that I would predict other words from the vocabulary that aren't in a context of a particular word, x of j. Right? So that's what this is doing. This summation is over all other words in the vocabulary. That's not feasible, right? You have a vocabulary, it's in the size of millions, even tens of thousands. Computing this is not necessarily efficient. It turns out that there's a great solution, and it's used not in just this situation, but in a number of different situations where the output space is quite large. So in classification tasks, let's say, where the set of classes that you're trying to predict is not necessarily, a dozen or so, but maybe on the order of tens of thousands or millions, you need a trick like this as well. And the idea is to just sample. So don't have this summation over all the words in the vocabulary, but just have it over some of the words. You randomly sample some of the words in the vocabulary, and you just make sure the objective function is satisfied with respect to that. So it's an approximation, but it turns out that in practice it works pretty well, and it turns out in practice that usually if for every positive context you just sample one negative context for that particular word, that's a pretty good thing to do. There is work about, like, okay, should I sample content words more than function words? And things like that, and can I do sort of adaptive sampling, like try to sample the highest scoring word that's not necessarily correct, and there's a huge amount of literature on that, but let's just, for simplicity, say, I have a word and some context, and I'm just going to randomly sample some other context, one word from the vocabulary that's not in that context. And that's my objective function. This, again, is differentiable, so we can use stochastic gradient descent or whatever to optimize it. And so this is basically word-to-vec, at least one incarnation of word-to-vec, the skipgram model, which I think is probably still the most popular incarnation in the literature. And just to point out, we are learning two representations of words. One as the word as its focus, right? So this would be the representation of brown as the focus, as well as a representation of every single word in a context. We care about the focus vector, and let's just throw away the context representations. And a very cute artifact, which was all the rage 4 years ago or 5 years ago, whatever, was that you could do like, you can have these like arithmetic artifacts. You can essentially say like, okay, well, take the word embedding for Greece and minus the word embedding for Canada minus Ottawa, and then find me the closest. So that gives me a new vector, and find me, of all the other words, the vector that's closest, by Euclidean distance or something like that. And you would get things like Athens, right? Because Ottawa is the capital of Canada and Athens is the capital of Greece. So there's this kind of like nice side effect that sort of showed the word that the embeddings were working. And there's some tools, I think, like, anyways, that's neither here nor there. Okay, so to get to an early point, Word2Vec is an example of like learning embeddings via language models, right? So essentially, we want to learn a representation for a word by predicting some context of that word. Often we think of language models as predicting the next word, but it need not be that case. It depends also whether you care that the model, is a proper probability distribution or not, and these things do come up. But it is kind of a simple example of like, okay, I'm going to represent a word by its ability to predict its context. And things like Elmo, BERT, XLNet, these sort of things that are in the news these days and you're going to learn about in subsequent lectures, these are examples of that as well. They're just kind of the 2019 equivalent of Word2Vec. You can think of them that way. And like I said, it's very powerful to think of these methods, since we don't need supervised training data to train them, to think of these methods as ways of learning representations for words and sentences using large amounts of unlabeled data, and then fine-tuning those representations on a specific task you care about. And really, like Elmo and BERT are sort of, I would say, the two most canonical examples nowadays of doing that. And that's what's kind of led in the past year or two to just massive jumps in accuracy on a lot of benchmark language technology challenges. So this is kind of just to prime you for some things that are going to come up later in the lecture. Not this lecture, the next one. Okay, so, right, static. So now we can train a neural network using Word2Vec. We can generate static word embeddings that way, and then we have a way of feeding the neural network. If we define the structure of the neural network, we know how to compute a loss and backpropagate that loss during training. So we have a neural network. However, sometimes we want to not just rely on static inputs, but actually learn these input values as part of training. So that would be learning this lookup table here as opposed to relying on Word2Vec. Well, that's quite simple, right? Essentially what you do is during backpropagation, the set of parameters, or the set of model parameters doesn't just include these purple nodes here, which are the linear transformation weights. It also includes the input nodes as well. These are just neurons, right? And so now we just need to compute the partial derivatives with respect to those values as well. They're part of the gradient, and you will learn this lookup table. And that's it. It's actually quite simple and elegant. Good. So I just want to finish off with a very kind of critical thing. We often don't just classify words in isolation, right? So we often care about classifying documents or sentences. So what do we do in that situation, right? Neural networks require as input a fixed length vector, right? Documents are not fixed length, of course. So, what do we do to kind of handle this case so that we can transform something that's not fixed length into something that is fixed length? Well, there's some naive solutions to this. One is to say, like, okay, well, yeah, documents can be any length, but I'm just going to say that they're no more than 200 words in length. So let's say I'm going to truncate every document at 200, and if the document's shorter than 200, I'll just pad it with some random words or something else. And then my input is essentially a vector that's of size k, 200, by the featured, the dimension of the input. So I just take all the words in the document and I just concatenate them together into this huge input vector. That has a lot of problems. Documents don't have a fixed length. It actually then, will, like a word occurring in different positions will mean different things, and we haven't really accounted for that in the modeling. So it also makes that input layer to the first hidden layer very, very large, a lot of model parameters, again, hard to learn. So we typically don't do that. A simple thing would just be to say like, okay, well, I'm just going to average them. If I have a bunch of word embeddings in a sentence and I want to create a fixed length representation for that sentence, I'll just average the word embeddings and then my representation is equal to the same dimension as words. And this is a type of what's called pooling operation. I'm going to talk about that in a second, and that's certainly a nice way to do it. It's kind of like a bag of words model, right? We don't, we sort of throw out everything we know about the position of the words in the document and just say, oh, we're just going to throw them together, average them, and learn something. And in practice, it'll work reasonably well. However, there are, you know, as usual, there are solutions, much more principled solutions to this problem. I'm going to talk about, in this lecture, convolutional neural networks. And I believe in lecture 3, we're going to get into recurrent neural networks, and in lecture 4, transformers, which are more convolutional in nature. But for now, let's look at convolutional neural networks. So this is a bit of a whirlwind tour, but I just want you to get familiar with the concepts. So here, this is our neural network. We have our input embeddings, as before, for the sentence. I'm going to throw some padding in. So basically, let's say I just have specific embeddings to represent the start and end of a sentence. This is a very common technique that people use in language, neural networks for language. So convolutional neural networks have what's called the convolutional layer. So basically, that's a way of taking that input and transforming it in some way to a bunch of other inputs. Now, I'll talk about what that is in a second. And a pooling layer, which is a way of taking all those outputs from the convolutional layer and merging them down to a fixed length vector, right? So the convolutional layer here is the layer that usually requires the designing. A very common one would be to say like, okay, well, I'm going to take some n-grams, some like fixed length words. So here we're looking at trigrams, so 3 words in a row. This is called the receptive field, basically how many parts of the input are you looking at. I'm going to pass them through an MLP, so this is just a neural network, a typical feed-forward neural network, and the output is going to be a vector of fixed length again. These MLPs are called filters in the literature. Sometimes you can have multiple MLPs producing multiple filters, or you can just fold all those filters into one MLP. That's kind of a detail. But essentially, we take a fixed set of input representations, and we map that down into a single vector, right? So this is like a trigram neural network, representing trigrams of the input. And what we do in a convolutional neural network, to account for the fact that documents are not fixed length, we just slide that convolutional layer down the sentence, and we get a bunch of fixed length vectors. And then the pooling operation just creates one fixed length vector for the rest of the neural network. And do I say it here? Oh yeah. Pooling, this last layer here, you know, people have looked at various possibilities, but usually averaging these vectors or taking the max, so the component-wise maximum of these vectors is a very common and usually good thing to do. One's called average pooling, the other's called max pooling. So there you go. However, as you can see, we're sort of still left with the same problem a little bit, that like, well, now this representation is, you know, before we said, well, it's not just good to average all the words because you get like a bag of words representation, you lose context. This way of doing it, we've said like, okay, now we essentially have a bag of trigram representations, which we average. So it's not exactly a bag of words model, but it's not sort of taking in a larger sort of global context of how words interact in the document. I'll skip this slide here because I think we talked about that. So very common is deep. So I think this is the first time I used the word deep in the talk, but these are deep convolutional neural networks. It's deep learning. We got there. And the idea is we can say like, well, okay, I hope you can read this. This is getting pretty small. This convolutional layer is as normal. It's a trigram convolutional layer. I get a trigram representation as the output. I can then do pooling, like a trigram pooling layer. So instead of pooling over all the representations, maybe I don't even need to do that. Sometimes this pooling step is optional. I sort of average these trigram representations. So already you're sort of increasing the scope of, you know, the model, the trigram scope or the contextual scope is already being increased here. And I can call this representation a convolutional block. And the key thing is, as long as I keep adding padding, I'm going to keep getting the same number of vectors, which is, you know, every single convolutional block, which is equal to the number of words. And then, essentially, I can just chain these convolutional blocks, as many as I want. I can have as many convolutional blocks as I want. And the more you have, because every layer I have trigram representations, and from there, I'm going to do another trigram convolutional network. So I'm going to increase my scope out to, what would that be, 5 grams. So I'll have like a window of 5 that I'm now considering. You can do the math yourself later. But every layer that I add, the contextualization of the model is getting larger and larger. So now I represent a word not just by itself or its local context, but the global context of where it occurs in the sentence. And then you do pooling on that. You run an MLP, the typical neural network we have for classification, and then you make a prediction. So this is kind of a canonical example of a deep neural network for text classification. There's other ways of doing this. I think this, anyways, this is a reasonable way of doing it. Okay, so just to summarize here, we focus mainly, so for neural networks, we focus mainly on feed-forward neural networks. What are neurons? What are layers? What are connections? The output layer and losses is identical to linear classifiers, right? The key thing is, from that, we can compute gradients through backpropagation, and then we can optimize the parameters of the model, which are these layer connections, using SGD. The input layer is where most of the action happens. Where do we get that? It can be static. We can learn it through something like word2vec. It can be dynamic. We just make those model parameters, and we let backpropagation do its work. Or we can combine them, right? We can first learn some word representations offline on a large corpus, and then initialize a classification model with those representations. And so a couple high-level questions. Right, so where does the structure come from? Right, so we've sort of said, like, all right, well, we have some dimensions and there's some layers and things like that, but where does that come from? Who decides on what that is? Well, these are hyperparameters. There is really no, I mean, there might be rules of thumb, but there's sort of no authoritative set of rules on this. These are essentially things that you try out empirically, right? You have some training data and you have some development data, let's say, some data that the model hasn't been trained on, and you just test it out. Try different architectures, different dimension sizes, different activation functions, things like that, and just see what works best in practice. The nice thing about this is that it can be automated, right? In a world of sort of cheap CPUs or high parallelism, we can just send this off and try a bunch of different values, like different number of hidden layers, different dimensions of those hidden layers, different activation functions. The product of all those is the sets of models we have to try out, and we just parallelize that and pick the best one. And sort of getting back to deep learning, which I'm sure you've heard a lot, deep learning is nothing more than neural networks where we have lots of layers, right? And that can just be lots of hidden layers, or in the last example I showed you, if you have like a convolutional block or some sub-neural network architecture, just having lots of that particular component. And that's deep learning in a nutshell. So do these models have to be fully connected? So we focus mainly on fully connected layers? Of course not. However, in practice, there's no reason not to. I mean, unless there's some specific thing about the task you're trying to solve that might suggest a non-fully connected layer, why not dense layers? In particular, even though they can be computationally expensive because they're not sparse, modern architectures like GPUs and TPUs really sort of negate any of those concerns because those architectures are specifically designed to do those kinds of computations. And that's kind of looping back around to that point with perceptron, where that was a machine learning algorithm designed for a specific architecture. And really nowadays, people who are on the vanguard of machine learning, that's what they're doing. They have a specific architecture and they're designing learning algorithms, and in particular, implementations of those learning algorithms specific to hardwares. Okay, so should you use neural networks? I think unambiguously yes. And I mean, I'm an engineer, and the main reason is they're better, right? If you have enough data, if you've pre-trained the model correctly, and you've done things the right way, almost certainly you're going to get a better accuracy. And in some cases, you're going to get dramatically a better accuracy. And we're not just talking, I mean, sometimes it's only on benchmarks, but a lot of times this is on real-world perception. So at the company I work for, Google, there was a paper a couple of years ago on deep neural networks for translation. Obviously, the offline metrics that they evaluate on went higher, but the main thing is they sat down a bunch of humans, as they usually do, and asked them to sort of grade the quality, and there was a dramatic improvement in their perception of the quality by moving to these networks. So I think unambiguously, yes, and also there's a lot of other reasons. You know, we can incorporate unlabeled data, right? Train word to vec, initialize models, that's great. That helps with generalization. Multitask learning, I didn't talk about it, but this is where you learn sort of multiple classifiers doing different things at once, and you can share representations, and this makes actually learning a little bit easier, and sometimes the classifiers get better. A major thing is that TensorFlow, PyTorch, DyNet, whatever, there's a bunch of tools out there that just make the barrier to entry much lower for neural networks than it ever has been. And so, yeah, why not use them? And you can always implement linear classifiers in these things anyways. Because, right, it entirely subsumes all the functionality of linear classifiers. One thing that's not true is that, oh yeah, we don't have to do feature engineering because we're now using neural networks, right? This is completely false. And now, first of all, I think this is me ranting. You're just going to have to bear with me for a few minutes. First of all, feature engineering wasn't hard nor time-consuming. I think there's sort of a misnomer that somehow that was like this cumbersome thing that people had to do. But when you look back at papers, most of them tended to use the same set of features anyway. So it wasn't like people were spending, you know, weeks and days, you know, whatever to do this. But it was also transparent, right? We knew what the features meant, right? So they said, oh yeah, well I have some property that says, oh, that there's an adjective in the sentence and it's next to a noun. And so I think that there's some sentiment towards that noun, right? That's something that I can explain, and when I learn a parameter for that, then it's easy to sort of say what the model thinks about that particular property. With neural networks, it's a bit harder, right? What do these layers mean? What do these neurons mean? There's a huge industry now around trying to actually tease that out from the neural networks through various means. These are almost all indirect because you really can't, you know, tease it out. It's not explicit in the model itself, but it's good work nonetheless. But I think the main reason why this is fiction is we're just sort of like moving things around. Before we thought about our input representations, now we think a lot more about sort of architectures and pre-trained representation. So we think about something like word to vec. You know, how do we pre-train it? Well, I have to define what the context is that it has to predict, right? And all these other ways of pre-training word embeddings are just defining different prediction tasks for learning these word embeddings from context, right? And that is designing features. So we've just moved that cognitive capacity from inputs to you know, how we design pre-training or how we design model architecture. So yeah, that's my people disagree with me, I'm sure, but that's my two cents on the take. Okay, so very last slide and then lunch. That was a lot for 3 hours. But we had to sort of get to a point where we can now get into the more advanced topics like structured prediction, recurrent neural networks, and then sort of, which are the foundation for really machine translation, question answering, all the sort of modern tasks that we try to solve in language technology. But getting back to this slide, really the things you have to understand are that we take an input, we represent it as a vector. That can be done through feature engineering to create sparse vectors, through dense engineering dense vectors through things like word embeddings, word to vec, things like that, or just back propagating through a neural network. Whether we're using linear classifiers or neural networks, you know, the difference is just in the number of layers. Ultimately, at the end, we predict an output. We take some loss. Those loss, whether it's a log loss or a hinge loss, it's the same linear classifier versus neural network. that we compute with respect to that loss a gradient of all the parameters in the model, and we use that gradient to set the model parameters, to iteratively update the model parameters. And that's it. I think everything else flows from these top level points. Good, I'll end there. Yeah.